Hello, everyone. Welcome to Google Automotive Partner Bootcamp 2022. My name is Kyung Ryu, leading the Global Partner Engineering for Automotive at Google. I'm here today with Gretchen Efkin, leading Global Automotive Partnerships. We'll share our journey of Android Automotive for its past, present, and future. Once again, our bootcamp is a virtual event this year. The good news is more people's lives are returning to normal. We definitely see the light at the end of the tunnel. I hope to be able to see you all in person very soon, and most definitely at next year's bootcamp. By the way, as a reminder before we show what is happening at the bootcamp this year, everything that we will talk during this event is confidential and shared under NDA. We'd love to have this bootcamp as a great opportunity to share Google's latest updates and roadmap with our closest partners like you. But we can only do that if you are able to keep them confidential. Thank you, and let's get started. I can't believe it has been already 7 years we have hosted this Automotive Partner Bootcamp. We are so excited to see the growing attendance from the various parts of the industry. Over 1,500 attendees from more than 80 companies joining us today. Thank you for taking the time to join us, and a big thank you to the team for making this event possible this year. Before we look forward, it's perhaps useful to look back at the road we have traveled together. Believe it or not, Google has been partnering with the automotive industry for over 15 years now. Our solutions have grown and evolved over those years. From the simple integration of Google Earth and Maps into proprietary in-car platforms in 2006, to introduction of Android Auto to leverage smartphones to power your car's infotainment system since 2015, to releasing Android that can run natively in a car in 2017. Then, Google Automotive Services and third-party apps were enabled in the vehicles in 2020. And very recently, the standardized digital car keys for Android phones have started mass production last year. We are so happy to provide these software platforms and build the ecosystem for our industry partners and developers like you, so you can create customer-focused automotive services and features to innovate the driving experience for your customers. Here is our bold vision that we were pursuing with the industry for the past 15 years. A safe and seamless connected experience in every car. It was not easy to move the needle in the beginning and took a long journey to get here, but we definitely see the industry momentum through various collaborations. For example, Android Auto, the phone projection product, continues to see strong growth and enhanced driving experiences for many, many people. It's now available in more than 150 million cars worldwide, with support from nearly every major car manufacturer. It is now even safer and more seamless by providing wireless connection and route information directly to an instrument cluster. Thanks to you and industry collaboration, AOS has also become one of the most preferred infotainment systems by car OEMs. It is also attributed to continuous innovation of the open source platform with various vehicle features and quality integration through mass production. Google has stayed the course to our commitment by providing partners and developers with the new features in new releases every year. Let's look at the past few years. We have added many key car features in AOS, actively listening to the industry demand. With early Android 10, car-specific power management services were enabled by adding suspend to RAM and garage mode. Then it has been further enriched through Android 11 and 12, with more granular network management and analytics services, as well as support for multi-users, just to name a few. There are more to be unpacked for Android 13, but I do not want to spoil the upcoming presentations. You'll definitely learn what it comes up with throughout this bootcamp. We have another big mission for the car industry. It is to transform the car software and services to make our cars better and safer over time with the system upgrades and the regular app updates. And it is really happening. We are proud to see Volvo recently roll out their second major OS upgrade to AOS 11 to their Polestar and Volvo cars, following the first upgrade last year. We'd love to work with you all to get the latest AOS rolled out to the vehicles on the road and provide newer and safer experiences to all the drivers and passengers. As you know, on top of the open source AOS, we have been offering some of the popular Google services for cars, also known as Google Automotive Services. With collaborative partnerships and Google's product investment, Guess also continues to grow strongly in the market. After Volvo's Polestar 2 launch with Guess in 2020, a few key OEMs have introduced gas-enabled cars in the global market, ranging from classic combustion engine vehicles to massive and futuristic EV trucks. Thanks again for your close collaboration to provide the best experience to the users, combining Google and third-party apps and OEM's branded design and customization. Just like AOS, Guess has been evolved quite rapidly. It provides innovative experience through frequent iterations. Guests are updated on a vehicle almost every month automatically. Assistant got faster and smarter. Maps enhanced EV experience for better routing, considering charging stations and energy consumption. And Play Store can perform download now and install later to cope with the limited connectivity and available bandwidth of a car. In fact, at this year's bootcamp, Google has opened up the guest partner sessions to all the automotive OEM attendees. Please join those sessions if your organization wants to find out more. We know that the innovative experience cannot happen only by Google Apps. It is more important to build a wide and healthy third-party app ecosystem to enrich the app experience in cars. We are happy to announce that many apps in the car-relevant categories like charging, parking, and navigation are now available in Play Store. In addition, we are working to make video streaming available on your cockpit, only when safe and parked. The seamless experience goes beyond the infotainment system. Your smartphone can make your daily activities more convenient and your life easier with less keys in your pocket. We have been working with our partners and standardization consortium to make your Android phone become a car key, which can be securely shared with others. After the launch with the BMW last year, we are working with many other partners to reach more cars and phone users to enjoy the digital car keys. In summary, Google and the automotive industry have come a long way together to build a safe and seamless connected experience in cars. We also witnessed that Google's commitment and our industry collaboration have made progress towards our shared vision. Now, let me hand this over to Gretchen and hear what's coming for the future.
Thank you, Kyung. Hello, everyone. My name is Gretchen Efkin, and I lead the Global Partnerships team for Android Auto. Excited to talk with you all today about building for the next generation of vehicles. As Kyung mentioned, over the last several years, we've worked together with you all as partners to support the acceleration of industry transformation. As connected, electric, shared, and autonomous technologies advance, we're working with the ecosystem on solutions for infotainment, telematics, sensor integration, ECU consolidation, and more. Eisenhower has often quoted these last few years for his famous saying that plans are worthless, but planning is everything. We've learned as an industry that the rigor of planning can help us think through scenarios, develop muscle, discover potential weaknesses, but we can't possibly think of every scenario. The acceleration of change throughout the pandemic has taught all of us to build in flexibility, reminded us of the importance of partnerships in particular. Bringing 3P ecosystems to vehicles is a complex task. There are many moving parts, many stages of maturity of development, and many players to align. But doing so is critical to success in order to build products that address consumer needs, particularly as we build vehicles that can be upgraded over the air with value added services, whether on a temporary or a subscription basis, that enable users to actually achieve value retention of the vehicle post purchase. And what about tomorrow? We have a lot more we can do together across a wide range of areas to deliver products to make the ecosystem stronger and better. We are shifting from a hardware centric industry to a software centric one. We're merging software across the vehicle and cloud, otherwise known as the digital chassis and digital twin. We're building end to end software defined vehicle solutions, from the EV skateboard up to cloud based apps and services ecosystems. With a centralized architecture and connection to deep car data in the future, deep data logging, perception, over the air updates will enable capabilities like ADAS and more. Use cases that cut across multiple sectors and areas that get better over the lifetime of the vehicle. The future of in-car software will enable a digital connected experience on screens throughout the car for drivers and passengers. Services from the car, the cloud, and brought-in devices like smartphones blend together for one seamless experience. Users won't have to know or care where the services are running, and they don't need to think about the technology behind the scenes. It will just work together seamlessly. Turn-by-turn maps that fuse autonomy and ADAS with lane-level navigation to give drivers a more helpful view of the world around them via Google Maps. Entertainment from your favorite content sources to pick up where you left off the latest episode. Games streamed from the cloud on services like Stadia. In-car productivity and social video experiences with services like Google Meet. We envision a future where the consumer's digital life flows seamlessly into the vehicle so they can access their digital services on the go. They don't need to plug in, sign in, or think about the technology behind the scenes. It just works to keep them connected, informed, and safe on their drive. We hope that you'll agree that this software-defined vehicle opens up the possibility of an incredibly exciting future. But to deliver those products, Google continues to focus on the fundamentals, ranging from privacy and security to reliability and connectivity, while listening to all parts of the ecosystem. Of course, our work is not yet done. The industry is moving full speed through simultaneous transformations in connectivity, electrification, autonomy, shared mobility, just an incredible amount of change happening all at one time. 7 years in the making, Android Automotive operating system shows Google's long-term commitment to help our partners move faster, more efficiently, while also helping partners deliver value to their customers at scale. Android 13, our sixth major iteration of Android Automotive OS, is coming out very soon, and it's packed with features ranging from better permission management and improved customization to providing enterprise APIs to unlock new use cases, such as fleet management. Over the next 2 days, you'll hear a lot more about advancements in a variety of AAOS areas. As we look toward the future, we continue to examine and invest into areas such as multi-screen, so Android continues to be the best operating system to power all of the in-cabin experiences while supporting a variety of related in-car experiences and use cases. Google services continue to evolve to fit your needs. We have heard loud and clear that while we have made great strides in enabling users to access their favorite services, such as Google Maps, directly in the vehicle, there are more things that we can do in a variety of areas to help you address pain points. For example, we are deeply engaged in enabling Google services to run across multiple screens and tailoring those services to make in-car experience feel truly seamless and letting the user experience your vision, even looking at ways to customize and bring your brand more forward into that experience. Having multiple screens or amazing interiors can feel like a blank canvas without having the right content and services that a consumer wants. Most recently, we've expanded into 3P categories such as maps, charging apps, and we plan to do more. This is why we are heavily investing into bringing gaming, cast, browsing, video, and a variety of additional use cases to make sure your customer gets the content they want directly from the dashboard. Thank you all very much for joining us today. Enjoy GAPB 2022. We're excited you're here. And let me turn it back over to my colleague, Kian.
Thanks, Gretchen. It is great to see so many things are cooking for the future. I'm sure my kids will love to play games and watch videos together in a car during a long travel. Let me briefly share what we have for you in the coming bootcamp. As usual, it's a packed agenda for 2 days with 4 tracks, where one track is specialized for guest production partners and future partners. It contains many presentations for new and advanced features in AAOS, as well as topics to help the partners for high-quality integration and streamlined certification of Android Auto and GAS. We also offer file-sized chats for open Q&A and breakout sessions for special topics. Thank you again for your time, your partnership, and collaboration. Please reach out to us if you have any questions or suggestions. We hope you all enjoy the bootcamp for the next couple of days, and we look forward to seeing you soon in person.
Hello, everyone, and welcome to the Google Automotive Partner Bootcamp 2022 session for virtualization. My name is Enrico Granata. I'm a tech lead on the team responsible for virtualization, and I'm here today to tell you all about the great work the team has been doing over the last year. Before we jump in, just a reminder that everything shared in this presentation is under NDA and it is shared with you confidentially. Please keep that in mind and respect the confidentiality. In today's session, we'll go through a quick round of introduction. We'll talk about new features in Trout 1.0, discuss release plans, share some of our forward-looking roadmap with you, and then have a quick recap. Let's dive right in. This journey began 2 years ago with the realization that cars are increasingly becoming computer on wheels. More and more advanced use cases are making their way into the cockpit. With that comes great opportunity, but also a risk for increasing complexity. At Android Automotive OS, we believe that virtualization is a key technology to unlock this potential and meet those challenges. Why? Well, virtualization can unlock the full potential of what we call the cockpit domain controller hardware category by enforcing clear resource ownership, allowing sharing but in a controlled and decided manner. And last but not least, allowing us to pick the right environment for each particular use case. Along these goals, we built a team and crafted a vision. Android Automotive OS as a performant, compatible, and open standards-based virtualized deployment by supporting and extending standards and delivering a high-quality reference implementation. Trout is that reference implementation. It is based upon Cuttlefish, which is Android's overall virtual reference platform, and it adds features that are specific to the automotive domain, such as vehicle HAL, EVS HAL, and others. Trout is supported on automotive hypervisors, and for many of its key features, it leverages the VirtIO open standard. By virtue of the way that trout is derived downstream of cuttlefish, almost like a subclass, partners are also free to extend trout and add their own features on top of the platform almost by subclassing trout itself. At a 10,000 feet level of overview, this is what a trout deployment can look like. We start with a host virtual machine, which is the only component whose kernel has access to physical drivers for the underlying SoC itself. On top of that host VM kernel sit VirtIO devices and services running either over gRPC or leveraging VirtIO console. On the Android VM side, we have the Android Common Kernel as the foundation. That does not include any drivers for the physical SoC itself. It all includes VirtIO drivers and services. On top of that kernel sit the Android HAL implementations, leveraging VirtIO console or leveraging gRPC as their communication interface. That is the only portion of the system that is Trout specific. Everything else that sits on top, framework, application services, that is vanilla ASP. That is one of the core architectural decisions that we made building Trout. That framework does not change. Trout offers a set of custom HAL and service implementations on top of which the framework and all the applications can run unmodified. What that allows is maximum app compatibility and portability. The other key tenet of the Trout implementation is that communication occurs through standard interfaces. Android and the host system only communicate through standard open source interfaces, be it VirtIO or gRPC. Why such a strong focus on open standards? Well, open standards allow a degree of vendor independence in the sense that if Android and the host are only talking to these standard well-defined channels, it's easy to take Android and move it from platform to platform, guaranteeing portability. It's also easy to take Android and move it from version to version, guaranteeing upgradability. Collectively, this enables a degree of compatibility where you can trust and rely on the foundation you're building your Android deployment on, and in turn, that enables a virtuous cycle of innovation and an open and thriving ecosystem. Last year, the team released the Trout 0.9 development ready platform alongside Android 11 QPR3. This release included support for core automotive features such as vehicle HAL, EVS HAL based on top of VirtIO video, support for sensors on top of VirtIO SCMI, and others like audio based on VirtIO sound and an implementation of audio control HAL. This year, we're happy to announce the release of Trout 1.0. We are sharing with you the Trout 1.0 production ready platform. The goals of the release include filling core feature gaps with native Android Automotive OS, achieving compatibility at the Android API level, and generally providing a baseline system that is ready for production usage. All the features that were supported in Trout 0.9 are also supported in Trout 1.0, and we're adding high-value improvements to the system with this release. Let's dive right in and look at some of those. In Trout 1.0, we add support for Bluetooth, leveraging ASP components, and HFP, leveraging VirtIO sound. GNSS is now available on Trout. We added support for Vulkan, leveraging GFX Stream. Trout 1.0 supports hardware vsync forwarding, providing more accurate rendering and smoother UI flows. The API of the Android platform is now compatible in Trout syntactically and semantically. Let's look at Bluetooth as an example. In Trout 0.9, we had integrated Bluetooth over VirtIO console, but due to some concerns around firmware initialization and vendor commands, we were still leveraging a custom vendor HAL for communication to Android. We were able to solve those issues in Trout 1.0, and we're replacing the vendor HAL with the ASP Bluetooth HAL. When you look at it, this allows Bluetooth integration in Android entirely based upon open standards. Everything that is running on the Android side is open source code. For historical performance reasons, HFP audio behaves differently from other Bluetooth profiles and other audio use cases on the system, it is generally handled as an out-of-band audio path. The challenge the team met when trying to integrate HFP in Trout was how to actually unlock these custom audio paths in a hardware-independent and generic manner. Our idea was to leverage ALSA-style controls through VirtIO Sound to manage external audio sources. For Trout 1.0, on the host side, we added support for a well-defined set of controls that essentially allow the host to tune in and out of that out-of-band custom audio path and let Android have access to it. All the Android guest has to do is detect the availability of those controls and actually tune them as necessary via Car Audio HAL and VirtIO Sound. While we only did the work in Trout 1.0 for HFP, this idea is broader and more general and could actually apply to any external audio source. For example, a CD player or even broadcast radio and others. I do not believe I can overemphasize how important the car is as a tool to get from point A to point B. We're making it easier in Trout 1.0 to achieve that by adding support for GNSS to the platform. We're leveraging VirtIO console and the AOSP GNSS HAL as a way to exchange location information between host and guest. When we looked at the data representation, we initially considered an MEA. But given the breadth and the depth of that representation and the specific narrow needs that we had for this use case, we actually settled on a comma-separated format, which was already used by the HAL itself and is also made available via the GNSS Logger app by Google, available on the Play Store. In Trout 1.0, we are able to share raw measurements and location fixes between the host and the guest. And we're looking at adding assisted GNSS and block listing to a subsequent release of the platform. When it comes to graphics, we're all about Vulkan. Our long-term goal is to deprecate all OpenGL based and leverage GFX Stream and Angle Vulkan for rendering. We look at GFX Stream as a recommended para-virtualization solution for graphics, and really it has a lot to go for itself. GFX Stream can unlock flexible display integration by supporting DRM hardware composer out of the box, but also providing support for Ranchu when richer display use cases are warranted. By providing support for context types, GFX Stream unlocks multiple graphics virtualization solutions, all the way from software-based para-virtualization to running host drivers in the guest in cases where this is supported by the hardware and the vendor. And last but not least, GFX Stream is the solution of choice for the wider virtual Android ecosystem. Many teams within Google leverage GFX Stream already, including Cuttlefish and Fuchsia, among others. What this allows us to do is easier integration, richer support for continuous testing, and just higher responsiveness to partners' concerns. When it comes to compatibility, our goal is that the Android API syntax and semantics in Trout are compatible. This specifically excludes bugs that may occur at the host or hypervisor level. For performance, in Trout 1.0, we're looking at two key indicators: boot time and jank rate. Our goal is that these indicators be on par or better than Trout 0.9. For an upcoming release, we will work alongside the core platform team to define additional metrics and support them via Catbox, with a strong focus on critical user journeys and overall quality of user experience. But wait, there's more. Trout 1.0 runs on the Android Common Kernel version 5.10. This is in two ways an improvement over Trout 0.9. The team was able to move with relative ease from kernel 5.4 to kernel 5.10, highlighting one of the key advantages that virtualization brings to this space. But in addition to that, we were also able to move from a monolithic kernel to a modular kernel. In Trout 1.0, the kernel common tree is shared with the core Android Common Kernel from ASP and requires no modification. All drivers and features that are specific to Trout are implemented as modules, and they can be loaded via the vendor boot partition. For Trout 1.0, we're making the entire code base available in ASP under the Trout Android 12 5.10 branch. We're also working on a new integrated tracing system based on Perfetto. The server API is available in Trout 1.0 and it's ready for hypervisor partners to start supporting. The vision behind this new tracing system is to have a unified and integrated tracing collector that can gather logs and trace points from the host and the guest at the same time and collate them in a shared viewpoint that can then be analyzed leveraging Perfetto by the system integrator. The goal is that a unified system view can allow for easier analysis and deeper understanding of the system state, and it is something that we'll continue to work on in upcoming Trout releases. Last but not least, with Trout 1.0 comes a clear and actionable definition of what it means to be a secure Android Automotive OS guest VM deployment. How to get access to Trout 1.0? Trout 1.0 will be made available on Qualcomm SA8155P alongside Android 12 QPR3. It runs on OpenSynergy's Cocos hypervisor. Please watch for partner announcements for more details on SDK availability. New this year, on the same hardware and the same Android release, Trout 1.0 also runs on the QNX hypervisor. Please once again watch for partner announcements for more details on SDK availability. While the team couldn't be more proud and excited to share Trout 1.0 with you, we're also already hard at work on next steps, and I'm glad I'm able to share some of our forward-looking roadmap with you today. We have plenty of improvements to the platform that we're looking at, including support for security and specifically adding Trust Zone into Trout. That will unlock high-value improvements to the platform, such as Widevine, key mint, and other halls. We're looking at machine learning and more specifically, how to add an open standards-based API to the platform to allow MPU sharing between host and guest in a hardware-agnostic manner. We want development and debugging on Trout to be as seamless as plugging a USB cable into a phone. And we're going to look to how to improve the ADB tooling to make it so in an upcoming release of the platform. We're looking at other things, such as use cases where multiple Android VMs may need to communicate and how to make that data exchange safe and seamless. We're going to look into how to implement Health HAL on Android to bring flash lifetime monitoring to the virtual platform. And we're also looking to do even more with our kernel strategy, bringing GKI to virtualization. If you remember one thing from this session, Trout 1.0 production-ready platform will be available alongside Android 12 QPR3. Please try it out and provide us feedback. We look forward to hearing from you. Thank you.
Hello, everyone. So this presentation is about the AIDL vehicle hardware abstraction layer. My name is Yu Shan. I'm a software engineer in the AOS platform framework team. First, I want to have a gentle reminder that everything we share here is confidential and bound by our mutual NDAs. Please respect the confidentiality. Okay, with that said, let's get to the agenda. So first, we will talk about a little bit of overview of this whole presentation, and then we will talk about why do we need to migrate the vehicle health to the AIDL vehicle health. For the third part, we will talk about what is the new AIDL vehicle health. For the first part, we will talk about how you can migrate your existing implementation to the new one. Then we'll talk about some of our reference implementation to help you migrate. And finally, we will talk about the migration plan. So the first part is a little bit overview about the AIDL vehicle hardware abstraction layer, which we call vehicle health. The vehicle health, vehicle hardware abstraction layer interfaces defines the properties OEMs can implement for their vehicle. And the vehicle health interface is based on accessing, which means reading, writing, and subscribing to properties. So this is one property is an abstraction for a specific function. And the existing vehicle health is defined using the HIDL, which is Health Interface Design Language. But we have a new language for the interface called AIDL, which is Android Interface Definition Language. And we are migrating all the hardware abstraction layer from using HIDL language to the AIDL language. The new AIDL vehicle health is backward compatible in a sense that there's no change to the car API and there's no client behavior change. So it is somewhat backward compatible. And the existing HIDL vehicle health is still supported, but it is in maintenance mode. And no new properties would be added for the existing HIDL implementation. All new properties need to be added to the AIDL interface instead. We will talk a little bit about this more in the later slides. So here we show the architecture for the HIDL vehicle health and AIDL-based vehicle health. We can see that it's very similar. It only differs in some of the components. For example, it differs in the car service. There's a called little stub, which communicates through interface to the vehicle health. That part is a little bit different. And of course, the interface itself is different because it is defined in a new language. And the implementation for the vehicle health itself is different. So those three parts are the main difference. And the car service, along with the car API, remains the same. So there's no change to the application that uses the car APIs. Next, we will talk about why we have an working existing HIDL-based vehicle health and why do we need to migrate that to a new language. The main reason is that all hardware abstraction layer defined by HIDL language is deprecated. And we want to migrate all the hardware abstraction layer to be defined in stable AIDL language. The stable AIDL has the following advantages compared against the old HIDL language. First is that AIDL is used in other places, not just the hardware abstraction layer. So it's better to have one IPC runtime within the Android stack. And secondly, the stable AIDL supports better versioning compared to HIDL. So all new health interfaces should be defined in stable AIDL. And that's why we want to migrate the vehicle health as well. And also, we are using this chance to support new features because this is a completely new interface. This is not a new version of the old existing interface. So we can take the chance to add new functions and modify existing functions to support new features. Next, we will talk a little bit about what is the new features that is introduced by the new AIDL vehicle health. There are mainly three new features that are added. The first feature is called batched operation. So in the existing interface, we only allow setting or getting one value in one function call. But in the new interface, we now allow setting and getting multiple values in one function call. So this would cause less overhead because you will need less RPCs. And also, we allow large data size in one function call. So the binder interface has actually a memory size limitation. You can only send that amount of data in one IPC call. But in order to allow sending arbitrary large enough data, we now use shared memory file to allow passing large data. This combined with batch operation allow you to, for example, get 100 of properties in one function call. And thirdly, we also support asynchronous operations. Asynchronous operations mean that you don't have to block, the caller does not have to block on the result. It does not have to wait for the result, but it can just pass the callbacks to the functions, and it can do other stuff. And when the result is ready, the result will be delivered through the callbacks to the caller. So the caller is not blocked. To demonstrate this in a graph, the existing flow for get value is like this. The vehicle health client send one request. You only allow one request in one API call to the vehicle health. And then it's just blocked on the result. It cannot do anything else. It's just waiting. And when the vehicle health has the result, it delivers the result as the return value to the function call to the vehicle health client. And the client processes the result. In the new flow, we now have this. The vehicle health client now can send multiple requests in one call. So for example, here it sends 3 requests or 3 requests in one call. And then after it sends the request, there will be a binder thread in the vehicle health that is processing the request. It would register all the requests to another thread called the handler thread and immediately return OK to the client. After client receives OK, the client is free to do other things. It does not need to be blocked, even though the result is not ready. And the binder and the handler thread in the vehicle health will actually process the actual request and send them the request to the vehicle bus and wait for a result. When the result arrives, the handler thread would use the callback to deliver the result back to the client. And then the client can pick up the result and process the result. This is the new iVehicle health AIDL interface. The file is called iVehicle.aidl. This lists some of the functions, not all. For detailed documentation, please check all the comments at the file iVehicle.aidl and see the link. Here are some of the example of some of the functions. For example, first we have the get all prop configs. This function get all property configs. And the second one is get the property configs for some specified properties. And then we have get value and set value. But note that here the get value and set value does not return anything. Instead, it takes a callback as an argument. So this function might return without the result being ready, and the result would be actually delivered through the callback interface. There are also subscribe and unsubscribe functions. This is similar to the existing HIDL interface. Subscribe is that you start monitoring value changes for a list of properties. Unsubscribe is unsubscribe previously subscribed properties. One function we add is the return shared memory call. This is used in case where the vehicle health implementation might want to use shared memory file for subscribed properties to deliver a property update event. For example, if I subscribe to property 1 and it is updated very frequently, the vehicle health implementation might want to just allocate one shared memory file for these property value changes and deliver this property value changes through that shared memory file to the client. But the problem with that is that the vehicle health needs to know when the client has finished reading the value so that the vehicle health can write new values to it, so that we add this return shared memory function that should be called by the client after the client has using the memory file used in property events. It's basically telling the vehicle health that I have finished reading my reading the values from this file, so now you can start writing a new value to it. This is the callback interface. So it is the interface that used to deliver a result asynchronously. it contains the following functions. One is on get values. So this is a callback that's just supposed to be called when one or more results or get values are ready. So even if part of the results, for example, if you send 3 requests, even if part of the result is ready, for example, I have the result for request 1 and request 2, the vehicle help can use the onGetValues callback to deliver part of the results. The client is responsible for tracking all the results is ready. Similarly, if we have onSetValues, and this is the callback to be called when one or more results for the set values are ready. We also have onProperty event and onProperty set arrow. These 2 callbacks are used for subscription. It is used to inform the client when a property update event happens or when a property set operation failed asynchronously. This is usually caused by a property set failure message from vehicle bus. Next, we will talk about how you can migrate your existing HIDL vehicle help to the new AIDL interface. To define a new AIDL vehicle help service, you can use the following interface definition and use the following service, the following build rule for your service implementation. So here's the reference service implementation CC binary rule. You can copy that, but with your own name and with your own source files. Note that you must use this shell library called libbinder_ndk because you are actually implementing the ndk service backend, not the CPP backend. And you must use this libbinder_ndk, not the libbinder. The static library android.hardware.automotive.vehicle-v1-ndk is the ndk backend file automatically generated from the AIDL interface rule on the left side. So you should include that as a static libraries in your service implementation as well. For the VINTF fragments and the init.rc file for your service, you can see appendix. There's an example that you can just copy and use. There are several type changes introduced in AIDL. Firstly, AIDL service implementation uses standard types to replace Android-specific types. For example, it uses standard shell pointer instead of Android SP. It uses standard weak pointer instead of Android WP. It also uses standard vector instead of Android-specific vector types. You can check the link for details. And also, the namespace is a little bit different. In the HIDL namespace, because we are actually using version 2, so it's Android : hardware : automotive : vehicle : v2_0 namespace. But now we are changing to the AIDL namespace. There's also a major difference is that the AIDL vehicle help is using one AIDL file for one type. So it will generate one header file for one specific type. For example, for vehicle property, it is defined in the vehicle property.aidl file, and it will generate one header file called vehicle property.h. Similarly, for other types, for example, vehicle gear, it will generate vehicle gear.h. So in order to use all these types, you need to include all the header files that you want to use. For example, if I want to use vehicle property type, I have to include vehicle property.h and also using that name, vehicle property from that AIDL namespace. We have a helper header file called vehicle help types.h. It includes a lot of header files that you might want to use. So you can just use that header file instead. For example, if I want to use vehicle prop value and vehicle gear, they are all included in the vehicle help types.h. I can just include that one header file, and then using all these two separate types in your service implementation. Vehicle help utilities also contains many other useful utilities for your VHEL implementation. For example, we have the toInt function that converts an enum type to an integer type. So you might also want to use vehicle help utils in your implementation as well. All the types defined in vehicle help is AIDL vehicle help is exactly the same as the HIDL one, except for the following. We removed the subscribe flags in subscribe options because there's no current usage for that. And also the user flags is now defined in not in userflags.aidl, but in another AIDL file called userinfo.aidl. The main reason is that the user flags is supposed to be a flag rather than an enum. The difference between a flag and an enum is that a flag can contain multiple values all together. For example, you can have a user flag that is both system and admin. So it's actually an integer type. The user flag can be an integer type that is a user flag system all together with user flag admin. There's also some renames. We rename the raw value in vehicle prop value to raw prop value. And also we rename the bytes to byte values. In order to test your new AIDL implementation, if you are using our reference code, you can add unit test for iVehicle hardware implementation class. We will talk about the reference implementation later. And also the VTS test works with both AIDL and the HIDL vehicle health implementation. There are two functions there, two tests there. One called use AIDL backend, one called use HIDL backend. One of them would be shown as skipped if the specific backend is not available. Note that AIDL, if both the backend is available, AIDL backend has a higher priority. So the AIDL backend would be used. So if you have both backend installed, you will see the use HIDL backend be skipped, and the use AIDL backend be enabled. To help partners migrate their existing implementation, we also provide a reference implementation, which is a fake implementation that doesn't communicate with an actual hardware, but instead relying on an in-memory map to fake a real vehicle health. So the reference implementation has the following components. Firstly, we have the vehicle service.cpp. This is the reference vehicle health main function. It actually relies on a main class we call default vehicle health. This class is the main class to implement the vehicle health interface, and it contains generic logic for all vehicle health implementation. So vendor can decide to use this default vehicle health because it is supposed to be generic. And then we have a vehicle-specific class called iVehicle hardware. This class is device-specific. It is an abstract class that provides common operations that vendor must implement. It should interact with a real vehicle bus and should be device-specific. As we have speak, the default vehicle health is the generic class. It provides generic logic that includes argument checks, asynchronous callbacks management. It supports passing data passed through shared memory. So basically, it will deserialize the data that is passed through shared memory. And if necessary, it will also serialize data and put it into shared memory and send it back to the client. It also supports subscription management in the sense that it will track all the subscription clients and deliver the property change events to the clients that are subscribing to this specific property. It relies on an iVehicle hardware class, which is a device-specific class for the actual operations. Vendor could use this default vehicle health as is, but with their own implementation for the iVehicle hardware class. The iVehicle hardware class contains the following functions. It contains set values, get all property configs, dump check health, and update sample rate. It might look similar to the iVehicle.aidl interface, but it's different in the sense that it's simpler. For example, in the set values here, the function only takes a set values callback instead of a very complicated callback function that contains a lot of functions inside it. It only contains one callback that is basically a function with a result as an argument. So here it defined as set values callback. And you will not see any shared memory here because all that logic is already dealt with in the default vehicle health layer. Here, you will just receive a list of requests, and you are supposed to deliver a list of results through the callback interface. Note that because this callbacks is asynchronous, so the callbacks passed through in the argument is passed using a shared pointer, and this callback can live longer than the function's lifetime itself, meaning that you can store this callback in some global arrays or global data structures, and let the callback still being alive even after you return value for this set values function. Similarly, for get values is similar. Another function I want to mention here is this app update sample rate. So this function is used to inform the vehicle bus that I want to sample these properties for this rate. This is used for continuous properties, meaning that the property value is constantly changing. For example, vehicle speed. If the client is subscribing to vehicle speed at 10 times per second, then it will call the update sample rate with 10. So the vehicle bus should pull at 10 times per second for the vehicle speed. If another new client is requesting to subscribe at 20 times per second, then the update sample rate will be called again with 20. So you should update with a higher sampling rate. If the second client unsubscribe, then the update sample rate will be called with 10 again, meaning that you can now sampling at a slower rate because now the client doesn't require that faster speed. Note that this function is optional in the sense that if your vehicle in HAL implementation or your vehicle bus protocol only supports sampling at a static rate, for example, I can only subscribe to a pull at the vehicle speed data at 20 times per second, there's no control over that, then that is fine. You can ignore this update sample rate and just always polling at like 20. Even if the client only asks for 10 per second, you can always polling at 20. This is a comparison between the existing reference implementation and the new AID of VHL reference implementation. We can see that it's very similar in the sense that it all have the vehicle health client talking with a generic class through the interface, and then we have a device-specific class. The only difference is that we rename the generic class from the vehicle health manager to the new name default vehicle health. And we used to have a device-specific abstract class called vehicle health. Now we rename that to iVehicle hardware. But these two are very similar. You can see that they all have similar functions. Like get all property configs is basically the same as the list properties. Get values is basically the same as get. So you can basically just port your existing vehicle health in .java .cpp implementation to your new iVehicle hardware implementation. We also provide reference implementation for the iVehicle hardware class. We call this fake vehicle hardware. You should not directly copy this because this is device-specific logic, and all our fake implementation does is basically just using an in-memory map hash map. So reading and writing property doesn't do anything. Write a property is basically just write a value in your memory, and you will read that value out. That's basically all it does. It also contains some special logic for setting and getting some special properties, but they are all mostly for test only, and you should not directly use this. The fake vehicle hardware does not contain any interaction with any real vehicle bus. So you should modify this class and add logic to interact with a real vehicle bus. This is an example flow, basically the reference implementation flow for set values. So you can see that the client sends a request, right, to the vehicle health for set values for two properties, because now we support setting multiple properties. So it wants to set two properties at one function call. And then the vehicle health implementation, the default vehicle health, which adds the set value request to a pool, and then immediately return OK to the client. So telling client that now your request is being processed, now you can do something else, although the result is not ready. And then another thread, the handler thread in the vehicle health, will actually getting the request from the pool and contacting the fake vehicle hardware to get the actual value, and then deliver the value through callbacks to the vehicle health client. This is an example for another possible implementation for vehicle health implementation, which is event-based. The difference between this implementation and the previous implementation is that unlike the previous implementation, the request is sent to the vehicle bus when handling the request. So you can see when the vehicle health receives a set value request from the client, it immediately sends a set value request to the vehicle bus. but it doesn't wait for the result. It just returns OK. And then there's similar to the previous approach, there's also a handler thread. But this time, the handler thread is only listening result or messages from vehicle bus. So if it sees a result is ready for a specific request, then it delivers the result back to the client through callback. This implementation will require that your vehicle bus protocol is asynchronous, meaning that you can send a request to your vehicle bus, but you don't have to block on the result. If your vehicle bus is synchronized, meaning that when you send a request, you must wait for the result, and then you cannot use this approach. You have to use the previous approach, which is using event handler thread and sending the request and result in the handler thread. Next, we will talk a little bit about the migration plan for AIDL vehicle health. So we are working on the vehicle health interface and the reference code for possible inclusion in T release. We have already migrated all the existing vehicle clients to support both AIDL and HIDL backend. So for all the clients, they expose the same functions and they don't care whether the AIDL or HIDL backend is enabled. They have a common logic to deal with the two different kind of backends. So replacing your existing HIDL VHELP with a new AIDL VHELP should cause no behavioral change. All your clients, all your applications should work as is. For all new vehicle health implementation, it is strongly recommended to implement the vehicle health as an AIDL service instead of HIDL. And for existing implementation, it is recommended to migrate to AIDL. All the new properties from now on must be added to the AIDL interface only, meaning that the HIDL interface will be frozen, and in maintenance mode, there will be no changes to the HIDL VHELP interface. We will not add any new properties to the HIDL VHELP interface. And your HIDL implementation must not use those new properties that are only added to AIDL interface, meaning that you must not support properties that are not defined in your interface. To conclude is that if you want to add new property support, you have to migrate. That is why migration should be done as soon as possible. So that's all I want to talk about today. Thank you. And for more information, you can see the appendix and see the comments at the ivehicle.aidl interface.
Hey everyone, thank you for coming to the Google Automotive Partner Bootcamp. Today we'll be talking about new VHELP properties in Android T and Android X Vehicle Actions API. To give a quick introduction, my name is David. I'm a product manager on the Android Automotive team. Just a reminder that everything shared in this presentation is under NDA. So in terms of a quick overview of the agenda, today, first I'll give an overview of the Vehicle API product area. Then we'll spend some time talking about the new vehicle properties in Android T, which includes fog light properties, EV properties, trailer properties, and also weight properties. Finally, we'll close off by talking about Android X. What is Android X, why Android X, and also the specific APIs that you can use. First, I'll give an overview of the Vehicle API product area. So to put it simply, the Vehicle API product area essentially connects vehicle hardware to applications. So in this case, vehicle hardware is the gateway, which could be a CAN bus or SOM/IP. Within the Vehicle API product area, there's 3 different layers. We'll start with the bottom layer, which connects directly to vehicle hardware, and that's the VHAL layer. VHAL is the vehicle hardware abstraction layer, and it is the platform-defined hardware abstraction layer for vehicle data. That is part of Android and within AOSP. Parallel to that is the custom VHAL, which is the OEM-defined interface for vehicle data. It's very similar in functionality to the Android VHAL, except that this is completely proprietary and controlled by OEMs. The layer above that is the car property manager, which is a low-level library that provides access to car-specific information. Car Property Manager allows comprehensive access to all the properties within VHAL. And this is also within AOSP. The third layer above that is the Android X APIs, which we're introducing today, and it is part of Android X. It is a set of developer-friendly semantic APIs meant to be more user-friendly and easier to use than some of the properties within Car Property Manager. As you can see, applications can utilize both Android X APIs and Car Property Manager. The permissions model is based on what is defined by Android and OEMs for the VHAL, and these permissions flow through to accessing Car Property Manager and Android X APIs as well. So now let's jump into the new VHAL properties that we're adding in Android T. So for Android T, we've added 13 new vehicle properties that developers can now use in their applications. Within these 13 properties, there are 4 new property areas. The first new property area are fog light properties, and we're adding 4 properties there. The reason why we're adding these properties is to extend support to vehicles with front and rear fog lights. The second new property area that we're adding are 6 new EV properties. These properties were added to support emerging EV use cases. The next property area is 1 new trailer property. And the reason why we added this property is to help calculate more accurate speed limits. And finally, the last property area that we're adding is 1 new weight property. And the reason why we added this is also to help calculate more accurate speed limits. So now I'll hand it off to Nishta to talk about each of the specific properties that we're adding in Android T.
Thank you, David. Hi, my name is Nishta Ahuja. I work on GMS Core team in Android Auto. I'm a software engineer that also developed some of the properties that we'll be talking about in this segment. So let's get right to it. We're talking about new VHAL properties that were introduced in Android T. We have divided this into certain categories, and the first category is fog light properties. There were 4 fog light properties that were introduced as part of this segment. The reason why these properties were introduced was because we just had properties that gave control over all the fog lights together, but we needed more control over the front versus rear end of the fog lights. Therefore, we introduced 4 properties. The first one is front fog light state. It's a property that returns the current state of the front fog lights. It's a privileged apps property that can be accessed by providing car exterior lights permissions. The rear side of the property is called rear fog light state, which is essentially a counterpart of the front fog light state property. It provides access to the current state of the rear fog lights. It has the same set of permissions. It's a read-only property and can be accessed by privileged apps by providing car exterior lights permissions. These 2 properties can have these permissions. They could be on, off, or daytime running. The daytime running state allows the user to activate fog lights manually, whereas the on or off provide as the name suggests. The next property is called front fog light switch property. This property lets you set the front fog light switch to on or off. This property is read and write accessible, but requires control car external lights permissions to do so. And this could be used in automated light control apps. The rear counterpart is called rear fog light switch, which again has the same permissions and can be accessed by privileged apps, could be read or could be written. These two properties can have these values: on, off, daytime running, or automatic. The automatic setting allows the engine control unit to set the lights automatically, and the others are same as before. That covers the fog light section. Now let's move on to EV properties. There were 6 EV properties that were introduced in this segment. The first one is EV charge current draw limit. This is essentially the threshold that is set by the user, which tells you how much maximum current you could draw in amperes. This property can be read or written by 3P apps and privileged apps respectively by providing car energy and control car energy permissions. This can be used in navigation apps to find compatible chargers. The second property is EV charge percent limit. This is essentially a counterpart of the previous property, but in this you specify the percentage from 0 to 100. Again, it's the maximum charge percent threshold that is set by the user. This is also the read and write property that has the same permissions as the one before. This can be used to improve routing suggestions for long route trips. Third one is EV charge state. This property tells you what is the current charge state of the car. It's a read-only property and requires car energy permission. This can take the following permissions: unknown charging, fully charged, not charging, or error. This actually helps you understand what is the state of the charge, if it's charging or not, or is it completely charged or not. Next property is called EV charge switch, wherein you could tell it to turn the EV charging on or off. It could be read or written by privileged apps and requires control car energy permissions. This could be used to remote control the car for charging purposes. The next property is EV charge time remaining. This would tell you the estimated charge time remaining of the car in seconds. It's a read-only property and requires car energy permission to be accessed. The use of this car could be in entertainment apps to find the videos that fit with charging time. So if you're sitting idle, you could just play on the app, for example. The next property is EV regenerative braking state. This property would tell you the current state associated with the regenerative braking setting of the car. It's a read-only property accessed by 3P apps and requires car energy permissions. This property can take these values: unknown, disabled, partially enabled, or fully enabled. The next segment is trailer properties. There was only one trailer property that was introduced in Android T, which essentially tells you if the trailer is present or not. It's a read-only property accessed by privileged apps and requires privileged car info permissions. This property is particularly useful to find the parking spots for a car. For example, if there's a trailer present, you would need a bigger parking space. It can take these values: unknown, not present, present, or if there's an error. The last set of properties that was introduced in Android T, VHAL, is called weight properties. The property name is vehicle curb weight, where the curb weight is essentially the weight of the car without any cargo or passengers. It's a privileged apps only car, which requires privileged car info permissions to be accessed. And this property could be used, for example, to determine the speed limit for the vehicles, if it's carrying another cargo vehicle, for example. Now, we move on to the next segment, which is Android X Vehicle Actions APIs, which is the new set of APIs that were introduced in Android X. for which I would hand it over to my coworker, David.
So now we'll talk about Android X Vehicle Actions APIs. So what is Android X? Android X is a set of libraries that makes app developers' lives easier. The Android X namespace comprises the Android Jetpack libraries, and these libraries in the Android X namespace ship separately from the Android platform and provides backward compatibility across Android releases. There are three main benefits with Android X. The first benefit for developers is that it helps developers follow best practices. This means less crashes, less memory leaks, and the most recent bug fixes. The second benefit is that Android X helps developers reduce boilerplate code. Developers don't have to write the same code over and over again because Android X will have solved these problems with easy-to-use functions. The third benefit is that Android X helps developers write code that works consistently across vehicles and platforms. The reality is that sometimes, whether it's a different vehicle or whether it's different versions of the Android platform, there might be implementation details that developers need to take into account. With Android X, developers don't need to worry about any of those details and can let Android X focus on them. Just to close off here, Android X is open source and ships separately from AOSP. Currently, it already includes many libraries that make building an Android app easier. And we've recently extended that to automotive use cases with Android X Vehicle Actions APIs. So now I'll talk about why we're adding Android X for auto. So Android X Vehicle Actions APIs, we are moving from the left side of the slide to the right side of the slide. In the previous state, there was only VHAL and Car Property Manager. This means that applications had to use Car Property Manager for any vehicle information that they needed to access. In the new state with Android X APIs, we're adding an additional layer on top of Car Property Manager. And this means that applications, whether third-party, OEM, or Google, can now use either or both Car Property Manager and Android X APIs. Now I'll hand it off to Nishta to talk about the benefits of Android X for auto.
Thank you, David. Let's move on to the section where we describe why we needed Android X APIs for vehicle actions in the first place. These are the reasons as mentioned on the slide. The first one is developer-friendly APIs. As David mentioned earlier, we got some feedback on how Car Property Manager was not the easiest thing to use. So we thought about Android X. It provides more developer-friendly APIs, and if we can support all the APIs in this, we wouldn't need to use Car Property Manager at all. Second reason is open source and available for all apps. Android X is open source. So is Android. But unlike Android, this is completely independent and doesn't have the same release cycles. Any bug fixes could be made incrementally. The last and the most important reason is common interface for Android Automotive OS and Android Auto. The interface for the APIs is same across both the platforms. So if you would like to scale your app, this is the way to go. Like I mentioned about the common interface, as you can see in this figure, 3P apps and gas apps only need to use the same set of APIs, and they could access both the platforms. It makes it very developer friendly, saves a lot of time and effort. It's pretty easy to use as well. But the question comes, when to use Android X? If you have everything available in Car Property Manager, why would you use Android X and vice versa? The answer is, if you would like to use all the apps together, all the APIs, 100% coverage is only provided by Car Property Manager. We are still providing support incrementally, so not everything is provided by Android X just yet. And if you want to access vendor properties, Car Property Manager is the way to go. However, if you need less control over your features, Android X is the easiest to use. If you want to scale it across different vehicles and releases, Android X is the way to go. And most importantly, if you want to scale it, if you want to use it across different platforms such as Android Automotive OS and Android Auto, Android X is preferable. Now let's talk about what all APIs were introduced in Android X. These are some of the APIs that were introduced, and they all fall in car info bucket. Things like model, energy profile, toll, etc. They provide a lot more information than what's written here. You could read about them in a couple of links provided on this slide. Things such as battery percentage, make, model, year of the car state, etc. All that information is provided in these APIs. There's also a link that provides sample code. You can go through these links for more information. However, we are planning to release more APIs such as sensors, climate, and cabin APIs. So keep an eye out for that. Let's dig into the code snippet now. How do we use these APIs? In order to use any of these APIs, you would first need to create an object of car info class. And in order to do so, you would need to create an object of car hardware manager. You could do so as mentioned here on the slide. Once you have the objects in place, you would like to create a listener for all the APIs that you want to use. There are a lot of them. You could either create listeners for just one API or all of them as your use case requires. In this example, we are using two APIs, model and energy level. You could create the listeners for them as shown on the slide. So once you have listeners in place, you could just use the APIs to get the values. For example, in this slide, you can see model API is called fetch model, and the listener energy level API is called add energy level listener. There are other counterparts as well, and there are also remove listener APIs, which you can use as you see fit. And this is how you use all the APIs. This brings us to the end of our presentation. Thank you for listening to our presentation. We appreciate and welcome feedback from developers. So please, feel free to reach out to your Google partners if you have anything else to share. Thank you.
Hello, everyone. In this session, we'll talk about car mainline. My name is Kyung, and I'm working in AOS framework team leading this mainline work. Everything in this slide shared in this presentation is under NDA, and please remember the confidentiality. Okay, so this is today's agenda. So we'll talk about overview, roadmap, architecture, and also I'll give you some further detail about what should be done in OEM side. This portion I will take over. Then we have other section, remaining section, talking more about partner impact and partner requirements that will be covered by our PM. So first, let's start with the mainline overview. So mainline is a module which can include multiple software components in Android. In car mainline, we are basically adding car API, car service, and other car stack into a mainline module contained as a .apex file. And when we do this, we can install this mainline module into all the Android platforms, which support the car mainline. So this allows us to install new car modules which are developed from new Android platform releases into all the Android platform. And with the mainline, we can actually separate our car stack development from core Android platform release so that we can add new features to car stack without updating or upgrading the platform. Then new features also include things like a new API, which we couldn't do it before. But now with the mainlining, we can add new APIs and we can add a new car service or new car stack features. And also it can include other things like bug fix or security fix. One thing for vehicle API or car API is that vehicle HAL, which is critical for car API, is not updated as it is HAL. And vehicle HAL is still something OEM need to update with a separate OTA. But currently we are working to define vehicle property update flow together with the mainline update so that, and this we can add a new vehicle properties so that OEM can support some new features by updating vehicle HAL. That work is currently work in progress. And in right side, you can see pictures. The yellow box car framework Apex module is the mainline module we are updating, while other parts of the platform like Android framework and HAL will not be updated by mainline. They need to be updated through full OTA. And next slide, by doing this mainlining, we'll basically switch our transition model because currently we are developing our features in one Android releases and OEM take that branch and use it and ship for production. It means that there can be huge gap in basically landing new features because OEM have to take that Android to be fully released, then they can ship it. But with the mainlining, we are changing into developing new features in separate mainline branch. And then mainline branch will have more regular release cycle than full Android, so that OEM can actually take new features in potentially short time, depending on the size of the feature. And with this happening, car framework team will mainly work on mainline branch to add new things and release fixes, and we'll slowly reduce our support for other platform branches so that we can focus on improving our code base from single code base. And for mainline, we support up to 2 older platforms so that one mainline cut from stable release will support 2 older Android releases so that OEM can take it in all the platform releases. And also all mainline related changes will be shared and pushed through AOSP and through partner guided so that partners can have access to them. And this is our roadmap. And our roadmap for mainline started with page 1. Page 1 is more kind of internal development, which is currently happening in T. So goal of page 1 is a car stack to make car stack mainline ready for Android T and plus. And in coming T QPR release, we'll add new features and new APIs so that we can really prove that we can install mainline from TQPR1 into original T and confirm that it's working. So that will be page 1, which will be finished in this year. Then page 2 will release mainline module, both source and pre-built form to OEM, and OEM can ship the mainline in their production image. this page 2 does not involve Play Store level update. Still, OEM need to do release production image while do full OTA to update car mainline module. And currently, planning is ongoing to identify the right timing and schedule, because we will set this up when we really have partners starting with the T development. And first iteration of this page 2 will focus on only car mainline module. So we will not release other mainline modules at all, and we will only release car mainline module. But as we go through subsequent iterations, we can add more mainline modules into our release. And lastly, page 3 is kind of our long-term vision, where we want to update mainline modules through Play Stores so that end users can have new features whenever the mainline module is updated from Play Store. But this is kind of a long-term vision, and we don't have any specific timeline for going to page 3 yet. We'll first focus on page 2, and once page 2 is in some good shape, then we look into the way to transition into page 3. So next slide is showing overall architecture of the car mainline and show all the components we mainlined. Here, all the yellow colored boxes are components that goes into the mainline from T. Also, we have a gray colored components which we want to mainline, add to the car mainline, but probably will be done in later releases. The most critical thing like a car API and car service is already all mainlined in T. And also there's white boxes which will not be mainlined. And those are kind of, we call it as a built-in, because those are kind of say components built in specific platform release. And from the top, car API also has basically counterpart of API called car built-in. That's the API we use to help car API and car service to use some platform features. And these are intended to be car stack internal only. And car service is also split into two components. We split car service into built-in car service and updatable car service. I'll give you some further detail about that split later. And lastly, HAL components again. All HALs can be only updated through OTA. And if some new feature requires vehicle HAL update, it means OEM also need to provide OTA update to actually to support the new features. But there will be also other features which does not require new vehicle HAL, and those features can be supported as soon as the car mainline module is updated. Okay, so this slide, probably we covered all of them, so I will skip. And next slide talk about car service level changes. First thing we made in car service is that we had to split it into two components, built-in portion and updatable portion. So updatable portion has permission and also support for all your API, and it has all your features, while built-in portion allows the car service to have a system UID access for the system. And another change we made is the UI, because the car service had some UI like blocking activity for driving safety, and we moved these UI from car service into car settings and system UI, because we see the need to customize those UI from OEMs, but having those things sit inside the mainline makes it hard to customize those UIs. If OEM want to customize those UI from T, they need to look into car settings and system UI. And another thing is the resource overlay or car service configuration. Before mainline, we are using build time overlay, resource overlay to configure car service for OEM specific needs. That thing is no longer work with the mainline, because we can build the mainline only for one generic configuration, and then it should be configured for different cars. For that, we are supporting RRO to actually allow OEM to configure car service through separate RRO package. And there's a separate section talking about this RRO, so please attend that session and check what are things OEM need to do to configure car service properly. Next slide talks about OEM's customization of car service, right? We've heard that some OEMs are making some changes with some patches to car service to meet OEM specific needs. But this patching of car service is very problematic for going into mainline, because if mainline is released from Google, then OEM either need to do continuously apply the patch, or they cannot basically apply those patches. So to solve that problem, we are essentially taking two approaches. First approach is we expect the OEM to send us patches through AOSP so that we review them, and if it makes sense to have those patches in common code, we'll take those patches so that OEM does not have to retake them again and again. But sometimes some patches or some change is only making sense for that specific OEM, and we may not want to take it into common code. For that situation, we'll add a new architecture. We'll define OEM's customization service, which allows basically OEM to have kind of plug-in to replace some policy inside the car service. This work is what we just started, so we'll give you some clear design when we actually work on TQPR, but by that time, we'll provide some kind of service and interface which OEM can implement for their own customized service. Next slide talks about hidden car API usage. So in Android, hidden API is an API where platform doesn't provide any kind of, say, future compatibility or future commitment. We are always saying that hidden API can be changed or removed at any time. But this is problematic with the mainline, because if we remove the hidden API suddenly, and there's any app that is using that hidden API from mainline module, then it can actually break the API and it can bring compatibility issue. Because of that, for all hidden APIs under Android.car namespace, Google will not change any of these hidden API added in T immediately. That's just kind of say minimum compatibility we guarantee. But in longer term, we'll migrate all these API into more official. Sometimes the API is good enough, so you may just make them into official system or public API. Sometimes those APIs are not good and we may need to deprecate them. But if we deprecate them, we'll provide some kind of say alternative API so that OEM can migrate. And in some cases, we may not find any OEM using those hidden API. In this situation, we may safely remove them. But in any case, when we add a new API to migrate, we'll at least keep all the API for 2 more Android releases so that OEM can have some time to do the migration. And lastly, there are some hidden API under com.android.car namespace. These are internal APIs and is not intended to be used by any external components. These are car service and car API stack only, and OEM should never use them. For these API, we will not guarantee any future compatibility, and still we can change them anytime. But most of these APIs are kind of utility. So instead of using these APIs, OEM can just copy these utility into their own code so that they don't have to use these APIs anymore. And next slide is giving you some example of how we'll deprecate hidden API. For example, in the first line, we are talking about, let's assume that there's a hidden API called car.hidden call in Android T. And in Android U, we decide to deprecate it. Right? So in next release, we add this new API called car.new call. And we'll say that this will replace existing car.hidden call. And we expect the OEM to migrate to all their apps to this new API in either Android U or Android B. So we give at least 2 releases to do the migration. And we'll keep this old API for a while until 3rd releases after deprecation, right? So basically, in Android U, where we introduce this migration API for the first time, and V and X, we keep the old API as it is. But in the next release, Android Y, we'll remove the deprecated API and we'll only keep the new API. Because OEM has migrated to this new API in either Android U or B, mainline module built from Android Y and which supports only Android V, X, and Y will be safe and will not bring any compatibility issue. So we'll basically do this kind of say timed deprecation flow to guarantee that there will be some kind of say compatibility for hidden API. But as soon as a new deprecation pass and alternative APIs provided, OEM need to do the migration in at least 2 releases to guarantee this kind of compatibility. Next slide is talking about version. Because we are releasing car API independent of main platform API version, we had to add our own version. For this version, we actually added 2 versions, major version and minor version. Major version represents which platform SDK this API was added, and minor version allows us to actually distinguish different platform SDK versions so that we can bump the API version independent of platform SDK. This separation of major and minor helps the apps to do some version check in simpler way in some cases. That's why we split into 2 versions rather than single version. And in platform side, we also saw the need to introduce a minor version. So we added this car.platform version minor int concept in car API. So this will be the minor version for the platform, which is car API, and also apps can use to check if some specific feature will be available or not. And for each car API, now there are 2 version information the API needs to tell. First information is from which car API this API was added. So the apps can check the car API version to know if this API will be available or not, right? Second one is from which platform, major, minor version, this feature is supported. Even if API is available, still the platform may not have all necessary things and the API may not necessarily work. So apps are supposed to basically check all these required version information to safely use the API. And car API version will be always higher than or equal to the current platform version. We don't allow installing all the car API to the newer platform. So car API version will be always higher while same with the current platform version. And minor version will be reset to 0. So minor version, whenever we start a new platform major API bump, it will reset to 0, but we'll basically keep increasing minor version. For example, in the example, in T, car API major version was 33 and minor version was 0. But in TQPR1, where we update the car API, we'll bump up the minor version into 1. Then when it comes to U development, we update the car major version to 34 and minor version will reset to 0. And again, this version update will only happen through OTA in page 2. But when you switch into page 3, car API version might be updated from Play Store, and apps may see different API version after Play Store update. Okay, next slide is about the version check. So there are all these versions. So what can app do to use the API safely, right? So basically, app developers should check the annotation I've mentioned before to use the API and should confirm whether that API is actually available or whether the underlying platform is actually good enough to support this new feature. And there are several utility methods we added, right? For example, car.is API version and list, car.is API and platform version and list. These basic utility helps the apps to check both the API version and platform version. If this version check sounds too complex, other thing apps can do is simply check the platform SDK version. For example, if some new API is added in TQPR1, then it's a guarantee that the new API will exist in Android U. So basically, in next major platform SDK revision, SDK 34, that API will always exist. So apps may just do one version check, the platform version check, instead of doing car API version check. So this can be the simpler way to do the version check, but caveat is that apps need to wait. Apps is essentially waiting for the next major Android release to use the new API and new feature. And lastly, if there are some new car manager API added in specific API release, and if that API is optional, then simply checking if that API is enabled or not, is car that is feature enabled. That can be just good enough to check before using that car manager API. So instead of doing version check, some API can be actually used in this way. Next slide talk about system properties to use the mainline. So this is what OEM need to specify. The first property is that read-only property version.platform minor. This specifies the platform minor version of the platform, and for each platform release, we define the correct value. And this value is currently defined in package service car.mk, or if OEM is taking this property, just inheriting this make file is good enough. If OEM is not inheriting this make file, then OEM need to copy the right value from this file into OEM's own product make file. Next property is that car service.package. This specifies the package name of updatable car service. Because of assigning updatable car service may have a different name, and we cannot really basically know all these potential names in advance. So instead of hard coding any of these names, we ask OEM product layer to actually specify this. For AOSP, currently this name is properties defined in package service car.mk make file again. If OEMs are inheriting this, there's no change necessary. If OEMs are creating their own product make file, they basically need to copy what is basically defined here. Okay, next slide is about signing car mainline module. So signing is not required if OEM is taking Google signed mainline release. So basically Google will give signed pre-built, and if that pre-built is shipped into product, then there's no need to do separate signing. But if OEM is not taking signed pre-built from Google, OEM need to sign it. And by default, the mainline module in AOSP is signed with a development key, which also has a private key included in AOSP. If OEM release it with that key, then some bad apps can use that key to gain some privilege from the system. So that's bad for security. So OEM must sign with their own key if they are not taking Google signed module. And to sign car mainline module at this moment, there are two APK inside. So both APK inside should be signed, and also Apex itself should be signed. In right side, there is some example of what should be done in product.make file and Android.pp file to sign it. In first part, there should be this definition of product certificate override to tell what certificate is overriding for those basically APK packages. And product packages should include the Apex module with basically different signing, and we recommend using different name for OEM signed Apex module to distinguish it from AOSP module. Then in Android.pp file, the app certificate for each APK should be specified. Next slide continues about all the detail about this signing setup. So in Android.pp file, there's this definition of Apex key. So Apex key defines what public key and what private key should be used to sign the Apex module. And then override Apex actually specify the whole signing structure for overridden or overriding Apex module. And important thing here is the base. Base component tells you that, oh, this mainline module com.android.car.framework is overriding com.android.car.framework mainline module. And you need to specify key and container. Key and container basically include all the certificate and necessary basically information to sign the key, sign the Apex module. So next slide is talking about updating car mainline module. So I said that, oh, you can install mainline module to Android platform and see new things added. So how do you see that happening? What you can do is that you can install car mainline module. First, you need to build it. Like second line, you build the com.android.car.framework module. Then you can simply ADB install that Apex file. But this Apex file is not effective until we reboot the system because the mainline module car service is changing some kind of say persistent portion of the system. So the installation cannot be effective until we reboot the system. Once the device is rebooted, then we can see that new mainline module is added. If we do artificial PM list packages and check where the code for this car mainline module is coming from, after installation, it's coming from data partition. Before installation, it's coming from system partition. So this is a way where you can actually check whether you have newly installed the mainline module or whether you are still using old basically mainline module, which was originally in the platform or system image. And that's it from my side. I'll hand over to Edward for remaining topics. Thanks.
Thanks, Kenyang. Hi, everyone. I'm Edward, a product manager for the Car Mainline project. I'll be covering our motivation behind this project, the benefits of Mainline, as well as next steps and partner requirements. So just to recap everything that we've discussed so far, the Car Mainline project enables to modularize core components of the AOS car stack and enable them to be developed and updated outside of the normal Android release cycle. There's three main points that I want to cover. One are the platform changes. So within the AOS platform, there are various changes we've done to support Car Mainline, including A, updating API surfaces, so the deprecation of hidden APIs and the introduction of new car API versioning. B, making core components of the car stack, including car service and car API, now in an updatable Apex file. And C, knowing that car mainline modules will be Google signed and that they cannot be patched, altered, or configured by OEMs. Two, from a timeline perspective, car mainline will be supported starting with Android T, where OEMs can ship Google signed car mainline modules with their production image. Three, from a scope standpoint, we plan to support more mainline modules beyond the car stack sometime in the future. The timelines for this are still TBD. And while all modules will still be optional for phase 2, OEMs are strongly encouraged to adopt mainline during T development. So what's our motivation behind this project? As a platform, we believe that faster system updates are a key advantage for both our developers as well as our users. A faster development lifecycle will lead to higher developer velocity to build, fix, and release features. It will also lead to less software fragmentation because there is a more percentage of users updated to the latest software. Next, it will lead to less bugs. We believe that faster bug fixes and less overhead will happen as a result of mainline. 4, it will lead to lower error budgets. The ability to quickly fix issues in a timely manner would lead to less risk and more flexibility, both from a Google and OEM standpoint. And 5, last but not least, the ability to provide more features and make vehicles less obsolete equals more user value to all of our end users. So here's a timeline of how long it takes for us to deploy new features from a platform standpoint. So currently the AOS platform takes 36 to 48 months to deploy features to our users. This is a very long timeline, and it's a significant bottleneck in terms of having our platform enable the best functionality that the users can see. So imagine if an OEM were to give us a feature request today. We would accept that feature request, start building it for Android U, eventually deploy the feature in AOSP sometime in 2023 when Android U is released. It would then go through a few QPR and LTS releases. And then finally, OEMs will then start building and beginning adoption for Android U a few years later. And then it would take another 1 to 2 years for Android U to be deployed to vehicles. This is an extensively long timeline. And what we're trying to do with the Car Mainline project is to significantly reduce this. So the Car Mainline project can decrease feature deployment timelines by 12 to 24 months. And so I shared with you the previous schedule of what it takes to deploy a feature. What you see here are the schedules for the mainline phase 2 and potentially mainline phase 3. In mainline phase 2, we see a feature requested being accepted, but within 3 to 12 months, the Android Automotive team is able to push the latest feature to the mainline AOSP branch. And once this is released, this is independent of any desert cycle, the new feature and or APIs, etc., will be available on AOSP. And then an OEM can then go ahead and pick up this feature, pick up the mainline module, integrate it and test it, and eventually deploy it to the Android U vehicles that they are supporting. From a mainline phase 3 standpoint, this timeline is even further reduced as the feature is developed through the mainline branch and then pushed directly to users through the Play Store. Keep in mind the updates will still be available and drop to AOSP, even if we utilize mainline phase 3. Car mainline also has a few additional benefits, including better support, security, and OS freshness. From maintenance and a support standpoint, the AOS platform team believes the reduction in complexity will enable faster bug fixes and resolutions. So without needing to maintain multiple branches and strictly maintaining bug fixes in the mainline branch, we can thereby enable faster fixes and faster updates. From a security standpoint, the faster deployment of security fixes is also there due to mainline. And finally, from a consistency standpoint, the consistency of OS implementation across hardware and the consistency of API implementation for developers are also a key benefit. So requirements. What are the requirements to really adopt car mainline? So first and foremost, patching and forking of the car stack would break car mainline, would block car mainline compatibility. Since one, we cannot guarantee API compatibility of non-AOSP implementation, and two, these new mainline builds will not contain any patches applied by vendors or OEMs. If OEMs need to customize car service or specific components of the car stack, there are two options here. One, AOS can intake and upstream patches on a case-by-case basis. And two, we can also help determine alternative options, including potentially a plugin architecture, RROs, or something else that we could potentially work with you to build to help meet these customization requirements. For either case, please reach out to your technical account manager and partner engineering teams to learn more. Second requirement, the removal of hidden API references. So currently, the hidden APIs will either be deprecated or upgraded to system or public APIs. So as a result, OEMs will need to, one, assess hidden API usage across their final build image, and two, remove any appropriate hidden API dependencies or references to keep the stack mainline compatible. So please reach out to your technical account manager or partner engineering support team if you have any high priority hidden APIs that need to be supported moving forward or have any questions, comments, or concerns. And three, finally, from a requirement standpoint, car mainline represents a new way of releasing and updating the platform and the system. So at the very least, this change in release management will require OEMs to maintain another branch to test or debug mainline. And from an end-to-end testing standpoint and release management standpoint, there's a lot of variants and changes that might be required. It will really depend on the OEM, the SOC, and Tier 1, the validation requirements that each OEM might have, any patches that might be required, and even updates that happen within a mainline build. From an AOS release plan standpoint, we will share more details about exact timelines and process later in H2 of this year. So just to recap, the car mainline project enables a faster model of system development by allowing integration of new car stack features without requiring to update the entire platform. To ensure car mainline compatibility, OEMs should aim to meet the requirements that were listed. So 1, do not modify mainline modules. 2, drop hidden API usage. And 3, have an updated release management process. And finally, we want to work with OEMs and partners on understanding challenges in updating car mainline. Please reach out to partner engineering or your technical account manager for any questions or feedback. Thank you.
Hello everyone, today I'm going to talk about car mainline resource overlay. My name is Mayank Garg and I'm a software engineer at Google. Gentle reminder, everything we share here is confidential and bound by our mutual NDA. Please respect the confidentiality. CDD GMS requirements are subject to change until finalized. Today's agenda is, first I'm going to talk about the overview for resource overlay. Then I will talk how to create RROs. RROs are runtime resource overlays. Then I will talk static versus dynamic RROs, and then the advantage of RROs. Finally, I will talk about the precedence order of RROs and debugging RROs. Overview. OEM must overlay car service resources to work with the car mainline. Prior to the mainline, car service resources were overlaid using built-time overlay mechanism. In built-time overlay mechanism, configuration file, for example, in our case, package service car has this config.xml file. This config.xml file was directly overlaid using some another XML file with the same folder structure, and built-time mechanism can update the resources based on the new XML file, and this is done at the time of building the image. RROs are runtime resource overlays, and they are required to overlay resources for car mainline module. Built-time overlay can still be used for other APKs, but as car stack is now mainline, they require using the RROs. RROs are like APK files containing only resources. There are two types of RROs, static RRO and dynamic RRO. And at this location, device generic car emulator, you can find a reference RRO. Also for this presentation, this is in continuation with the previous car mainline presentation. So this is in addition to the presentation we had earlier. So to support the RROs, we have to make some changes to the car service. First of all, as I mentioned, that all built-time overlay are not supported. So we have removed all built-time overlay and converted the required built-time overlays into RROs. Also, we have to add one overlabel.xml file, which is I mentioned on the right-hand side. This file has some important features. So first is overlabel name, which is car service customization. This information is used for creating RROs, like referring to this particular overlay. And then we have policy tag. In policy, we can define which partition can overlay the resources from this particular config file. And then we have the items. Items are the actual resources which can be overlaid. Now, any resource which is part of the config file but not part of the overlayable file cannot be overlaid by RROs. Now, I will talk how to create RROs. RROs is an APK file, and like any other APK file, it requires an android.bp and Android manifest file. So on the right-hand side here, I give an example of Android manifest file. Few things to notice here, that it should have an overlay tag. This tag means that this is an RRO file, and few important properties is like Android priority. The priority defines in what order of precedence one RRO will override another RRO, and it is important to define this property. Then target package in the case of car service, it will be com.android.car.updatable. This is the package for which an RRO is being defined. Then target name, this should be the same as defined earlier in overlabel.xml file. And finally, we need to define whether RRO is a static or dynamic. In this case, it is static equal to true, means RRO is static. Similarly, we have to also define android.bp file. In the android.bp file, we have to first the APK name. So in this case, the APK name is car service overlay emulator, then the resource directory and manifest. Now, as you might have remember in the car mainline presentation, that depending on whether Apex module is signed by Google or not signed by Google, the name of the package might be slightly different. So if the package Apex module or APK is signed by Google, the package name has this extra .google in the package name, and in that case, we have to update our RRO package target package name and package name to match with the updated package name. So to do that, we can use this override runtime overlay feature, and then we can define our target package and updated name for the RRO APK. Moving forward, the main purpose of RRO is to overlay some resources. So in our RRO, we will have in the resource folder, we will have a config.xml file and overlays.xml file. Overlays.xml file is to define mapping between original resources defined in packages services car versus the resources which is overlaid in the RRO. And in the config.xml file, we are going to define the new value of those resources. So in this case, in this example, these two booleans maybe have different value in the default configuration, but we are setting them as true in this RRO configuration. Overlaying XML files. So RROs can also be used to overlay XML files. Currently, as a resources, we have car UX restrictions map as a resource XML file. And to overlay this, we have to define this overlays.xml with the same type of item target versus value. So it defines the mapping between the original resources versus resources in RRO. And in this XML file, there has been some change from the previous car user restriction map. Previously, there used to be a namespace qualifier before the attribute. Like in the case of driving state, it used to be a driving state car : state. Now we have changed the formatting slightly here. We don't need to namespace qualifier. It would be driving state and then a state equals to park. So there is a minor change in the formatting. Moving forward, dynamic versus static RROs. So how to create static RRO? So the process of creating the static RRO is same as we described for any RRO. The only difference is that this Boolean value is static in the Android manifest file will be true, and if the RRO is static, then it is enabled at the boot time, and once an RRO is enabled and an static RRO is enabled, it cannot be disabled without the OTA. Static RRO in general are enabled by default unless there is some kind of a condition. You can enable them conditionally, and I'm going to talk about in the later slides how can we enable them conditionally. And we have this example of a static RRO at this location. So device/journey/car has some static RROs. Static RRO is a common way to overlay resources. How to create dynamic RRO? So the only difference between static RRO and dynamic RRO is this in the property in the Android manifest file. In the case of a static RRO, it is true. In the case of dynamic RRO, this property Android is static is false. There are some advantage of dynamic RRO. They can be enabled and disabled dynamically. So as I mentioned earlier, the static RRO are enabled by default unless they are conditioned, but this dynamic RRO can be enabled and disabled whenever you want. And another advantage is that dynamic RRO can be updated using ADB install or application store, while the static RRO cannot be updated. We think that dynamic RRO can be a mechanism to update resources after updating the module. And one example of dynamic RRO is given at this location, vendor/auto/embedded. Now, how to enable dynamic RRO for car service? As I mentioned that static RRO is enabled by default. For enabling the dynamic RRO in case of car service, we have added a system property for the list of dynamic RROs overlaying car service resources. And the property name is ro.android.car.carservice.overlay.packages. So this property, you can define all the static you can define all the dynamic RROs, and while we are loading the car service, we read this property, and whatever dynamic RRO is defined here, we enable those dynamic RROs. now only the qualified RROs will be enabled, and the qualification criteria is that RRO must exist. It must overlay car service updatable. So this mechanism cannot be used to enable any generic dynamic RRO. So the RRO must overlay car service updatable, and RRO from these partitions: system, vendor, OEM, ODM, and product partition. This is a security feature which is in line with what we see in the overlayable.xml file. There also in the policy we mentioned that only these partitions can overlay the resources for car service. In this example on the right hand side where I define this property, I'm giving these two RROs, but both of them are same. The only difference is that one is for signed car service updatable and one for not signed car service updatable, because as mentioned that if the car service updatable is signed, the name of the package would be com.android.car.updatable. So correspondingly, the RRO will also be a different name. But in this case, only one of the RRO will be loaded based on whether the apex is signed or not. And it's the same RRO in both packages. And so now advantages of RROs. So advantage of RROs. So first of all, after moving to the main line, the car service, car stack module is decoupled from the device. So and all Apex module are independent of the device. So we need a mechanism to decouple resource overlays from the module. So RROs is a very good mechanism to decouple resource overlay from mainline Apex module. And one RRO, so there's some advantage of RROs, like one RRO can target one application, but there can be more than one RROs targeting the same application. So OEM can have one RRO, supplier can have one RROs, and other vendors can have their own RROs. So by that, there can be multiple RROs targeting the same application. Now, RROs also provide us a finer control. First, like they have a policy tag. So using the policy, we can determine which partitions are allowed to do the overlay of resources. And secondly, the overlayable tag, or secondly, we have to define the items in the overlayable.xml file. So if there is a conflict, if you have some configuration in car service and we don't want it to overlay, then we may not define it overlayable.xml. So it provides us more control over what can be overlaid and who can do the overlay. Advantages of static RRO. So there are some advantages of static RRO which I already mentioned. There is one more advantage is that static RRO can have product variant support. What does that mean? So as I mentioned that static RRO is enabled by default, but they can be conditionally enabled based on some system properties. So in this example, I have two RROs, RRO1 and RRO2, and they have a condition. So the condition is that this system property ro.com.oem.product, this system property, based on the value of this system property, one of these RRO will be enabled. So if the system property is not set, then none of these RRO will be enabled. But if this system property is set to this supercar 22, then RRO1 will be enabled. And if this system property is set to flying car 25, then RRO2 will be enabled. Now, it will also, now one of these will be enabled based on the condition, but once any of the RRO is enabled, it cannot be disabled back without OTA. Advantage of dynamic RRO. So dynamic RRO doesn't support product variants, like they don't have inbuilt support for product variants like we have for static. But we can do a product variant support using the property I mentioned earlier. So this property ro.android.car service.overlabel.packages property can be used to dynamically enable and disable the RROs. So for example, what can happen, we can have multiple RROs in our image, and then we can define this property based on product variants that enable RRO1, RRO2, or whatever RRO we want to enable. And this decision can be made during boot up time using RC file or some other mechanism. Another advantage, as mentioned earlier, also the dynamic RRO can be updated and they can be enabled and disabled later on. One thing is dynamic RROs are required to enable on per user basis, but in case of the car service, dynamic RROs will be enabled for all users. Static versus dynamic RRO. So in general, static RROs are preferred unless RRO update is a requirement. Static RROs are more commonly used, so they are more stable. They support product variants and they are relatively easier to test. But if it is required to update resources after mainline update, we recommend using dynamic RRO. In case of car service, possible benefit of using dynamic RRO is enabling and disabling a feature, changing activity allow list, changing different wait times, and update car US restrictions. Dynamic RRO can be updated using application store, but it is currently not supported. It would take some time for that support, most likely a phase 3 of the mainline. But still, dynamic RRO can be added as a placeholder, and RRO must be signed so that it can be updated correctly via the application store. Currently, we are using one dynamic RRO, and rest of the device level RROs are static RROs. Precedence order of RROs. Now, precedence of order of static RRO is very important. Like when multiple RROs overlay the same resources, the order of overlay is important. Because you need a clear indication like what will be the final value of the resource. Unfortunately, due to some legacy code, the behavior of RRO precedence varies on many factors. To avoid the confusion and provide a deterministic behavior, we recommend that a static RRO should always define a priority, and the priority should be defined in this range based on who is the owner of the RRO. So if we are doing it in the Android, then we will define the priority in this range. If SOC vendor is doing, they should define in this range. For supplier, this is the range, and for car OEM, this is the range. Currently, we have no mechanism to enforce this range, but this is a recommended range so that things will follow this rule. So if these two rules are followed, then higher priority static RRO is going to override lower priority static RRO. Now, besides this, we in the debugging section, I will also talk about how can we see what RROs are currently overriding car service and what are their precedents. So we can also check it there if they are working in the correct order or not. Now, precedence for dynamic RROs. So dynamic RRO will always have a higher priority than any static RRO. Currently, we are recommending to only use one dynamic RRO, and to use that dynamic RRO, this property RO.android.car should be used to define the dynamic RRO. Now, in general, you might have to define two RROs, as I mentioned, one for the sign and one for not sign, but eventually it's only one dynamic RRO which will be enabled. Debugging RROs. So for debugging overlay mechanism, there are few shell commands. One is like ADB shell CMD overlay help that will give you all the possible commands. I'm going to talk about some common commands and how can we infer the results to understand more. So in general, we can use the ADB shell CMD overlay list, and we can define the user if you want. And this is going to give us list of all the installed packages who have any RROs. And it will also give the list of the RROs for that packages. And it will also give whether the RRO is what is the condition of RRO. So in this case, like I just put it as a demo for car service. So com.android.car.updatable, this is the target package, and this has two RROs currently installed on the system. The X means that the RRO is installed and it is active. Empty box means that RRO is installed, but it is not active, but it can be activated. And dash dash dash, which is not here, but sometimes if the RRO is installed and it contains error, then it will show dash dash dash. A common source of error is incorrectly configured manifest file or not or the overlays.xml file. So usually one of these two are the reason for some kind of RRO related error. To enable and disable dynamic RROs, we can use this command ADB shell CMD overlay enable and disable, and then the username and the RRO names. If you are enabling and disabling any RROs, to take that into the effect, you have to restart the car service. Now, as I mentioned that we have a mechanism to verify the order of precedence for RROs. So we can just do ADB shell CMD overlay list and then the target package. Now, this is going to list all RROs overlaying resources for this target package in the order of precedence. So like this is just for example, let's say I do it for car service and it has multiple RROs installed from everywhere. Then it will show them in the order of precedence, and you can see that the bottommost will be the highest precedence. And And the precedence is important when they are overlaying the same resources. So let's say the first one is overlaying resource A and the second one is overlaying resource B, then both of those resources will be overlaid and it doesn't matter what is the order. But let's say first one and the last one overlaying the same resources, then the last one will win. So that's why this precedence order is important. ADB shell CMD overlay dump. So this command can be used to dump all your target package and resources and also the mapping. So you can get the mapping from source, which is in the package services car config XML file to which of these resources are mapped to the RROs. There is a way also to look up the individual resources. Like for example, in this example, I'm looking for this rotary service. So there's this long command for looking how this resource, so like what is the value of this resource. So when we run this, we will see two things. One, from which package this resource is going to be served. So in this case, it is coming from the default package com.android.car.updatable, and what is its value. And like so similarly, in another case, when we are looking for this bug report application, it's saying that best matching is found from com.android.car.resources.vendor. So in this case, it is the best matching value is found in an RRO, and this is the value. So this lookup can be used to know what will be the final value of any resources. There are more tips, and this is publicly available links on this debugging for RROs. Now, as a summary, just to summarize the presentation, RROs are required to overlay resources for car mainline because the build time mechanism is no longer supported for after the mainline changes. And static RRO is the common way to overlay resources. And in static RROs, we must define priorities. RROs will override resources based on the order of precedence, and which is primarily depend on the priority. There should be a different range of priorities, as I mentioned earlier, also based on whether you are an SOC vendor, supplier, or OEM. And finally, dynamic RROs can be updated, enabled, and disabled dynamically. So that is the one advantage of dynamic RRO if you want to update or enable or disable any RRO after the release. So that is all. Thank you.
Hello everyone. Welcome to Car Framework Flash Memory Monitoring presentation of Google Automotive Partner Bootcamp 2022. Let me introduce myself. I'm Lakshman Anadurai. I'm a software engineer in the Android Automotive Framework team. This is a gentle reminder of confidentiality. Please remember that everything shared here is bound by our mutual NDAs. GMS and CDD requirements can change until finalized. Today, let's go over a brief overview of the Flash Memory Monitoring project. Then we will deep dive into user notification, application setting changes, launcher app implementation, storage monitoring API deprecation. Finally, I will end the presentation with a brief summary of today's presentation. Flash Memory Monitoring project was introduced in Android 12. The problem that you're trying to solve is that flash memory has limited write life and is expensive to replace in vehicles. Vehicles tend to be used around 10 years, which is much longer than any other Android form factor. When the flash memory wears off prematurely, the entire head unit becomes inoperable. For instance, a major OEM had to recall hundreds of thousands of their vehicles because of this exact issue. When their flash memory wore off prematurely, the entire vehicle became inoperable. Because it's expensive to replace in vehicles, when the failure happens within warranty, the OEM has to endure the cost of replacing the flash memory. The solution that we propose for this project is to limit the number of bytes returned to disk per application. To facilitate this, the Watchdog service monitors flash memory usage by all applications running in the system. GMS and OEMs can define flash memory overuse configurations. These configurations let GMS and OEMs limit the number of bytes allocated for each application. When an application exceeds the thresholds defined by these configurations, it is notified. The application must be registered with car service to receive this notification. Please refer to the 2021 Google Automotive Partner Bootcamp Car Framework presentation for more information on these APIs. When any non-critical application recurrently overuses flash memory, the user is notified when the driving conditions are safe. Then the application is terminated and disabled until it is used by the user. This prevents the application from being run in the background and abusing the flash memory. Now let's go over user notification. When an application overuses flash memory, the watchdog service notifies the app's resource overuse listener. The app must register with car service to receive this notification. When the app repeatedly overuses the flash memory, the user is notified when the vehicle is parked or comes to a full stop. On the right side, we have a screenshot of such user notification. For instance, when the Droid app repeatedly overuses flash memory, the user receives a notification saying Droid app is affecting your system performance. To improve system performance, this app will be prevented from running in the background. Prioritize app to continue using Droid app. The user is presented with two options. First one is OK. The next is prioritize app. When the user taps prioritize app, the user is redirected to the car settings page for this application. We will go over the settings page in the next slide. When the user taps OK, the notification is dismissed. The app will be terminated and disabled when the display is turned off. Now let's go over the application settings page. The per application settings page hosts a new item, which is prioritize app performance. On the right-hand side, we have a screenshot of the Droid apps settings page. There we have the item prioritize app performance, which has a subtext that says user system performance to prioritize app performance. This settings allows users to prioritize their application's performance over the system and long-term hardware performance. When the setting is toggled off, which is the default value, the app is terminated and disabled on resource overuse, including flash memory overuse. When the setting is toggled on, the app is not terminated or disabled on any resource overuse. The user won't receive any notification when the app overuses the system resources. Next, let's go over the launcher app. When an application is disabled on resource overuse, the application disappears from the launcher app. This leads to a bad user experience. On the right-hand side, we have a screenshot of the launcher app where the Droid app disappeared from the launcher when the app was disabled on flash memory overuse. We recommend the OEMs to update the launcher app implementation to show the applications that are disabled due to resource overuse. Here is a sample implementation as of SCV2. This is the recommended implementation for the launcher app as of SCV2. When showing the list of apps on the launcher must use the flag package manager match disabled until used components to fetch the list of disabled apps and show it on the launcher. When the user taps on an app that is disabled until used, the launcher app must use the package manager API set application enable setting and pass the flag package manager component enabled state enabled to enable the app before launching the app. Otherwise, the app can't be launched. As of SCQPR3, we have added car settings APIs that allows launcher app to get the exact list of apps that are disabled due to resource overuse. We recommend the OEMs to use this API from SCQPR3 onward. When showing the list of apps on the launcher, The launcher must use the car settings API. Car settings, secure, key packages disabled on resource overuse to fetch the list of apps that are disabled due to resource overuse. This API returns a string, which is a list of package names separated by semicolon. Similar to the previous recommendation, the launcher app must enable the apps before launching them. So when a user taps on any of the disabled apps, the launcher app must enable the app using the package manager flag, package manager component enabled state enabled. Next is the storage monitoring APIs deprecation. The car storage monitoring manager APIs are deprecated in Android T, except get pre-EOL indicator status API. All users of these APIs must be replaced with car watchdog manager's flash memory monitoring APIs. The car storage monitoring manager APIs will be removed in a future release. Finally, let's go over a brief summary of today's presentation. OEMs can optionally specify the flash memory monitoring thresholds. This allows OEMs to limit the number of bytes allocated for each app to write to the flash memory. Users receive a notification on detecting repeated flash memory overuse by any non-critical application. The users receive this notification when the vehicle is parked or comes to a full stop. Users can opt out their applications from being terminated on system resource overuse using the application-specific settings, which is prioritize app performance. OEMs must update the launcher app implementation to display apps that are disabled due to resource overuse. We have two recommendations. One recommendation is for SCV2, another one is for SCQPR3 onward. Then finally, majority of storage monitoring APIs are deprecated in T and will be removed in a future release. Thank you for attending today's presentation.
Hello, everyone. We'll talk about background X optimization for car in this session. And my name is Kyun-young, and I'm working in framework side of AAOS. And everything in this session is confidential. Please make sure that, please note that everything shared in this presentation is under NDA. So this is today's agenda. So I'll briefly talk about background X optimization before T. And then we'll basically show the changes we have made from Android T, and there will be short summary. First, background X optimization for before T. Right? So background X optimization is a kind of optimization of compiling text file from all APKs when system is idle. So this idle moment in car we define as a garage mode. So by nature, background X optimization will improve the performance of the app because we store this kind of optimized code instead of original text file. Besides X optimization, Android also supports JIT or just-in-time compilation for frequently used code. But note that JIT only kicks in when the same code is reused multiple times. So in the end, JIT will improve the performance for some code which is not used often, or for the first run until JIT is actually fully kicked in. The background X optimization is the way to basically guarantee some amount of performance for the app. And this kind of optimized code is stored in data partition. So if the user reset the data or do the factory reset, then it will delete all optimization and optimization need to run again. And before T, we had one problem for using background X optimization in car. The main thing is that this background X optimization holds global package manager lock. And this global package manager lock is also necessary when we do the user switching. So frequent problem we saw was that while background X optimization is running, if there comes user switching, then system sometimes goes into ANR because the lock required for user switching is not acquired for quite a long time. For some big package, this optimization can take up to a minute while system server can get ANR waiting for this lock in short time, like 10 seconds. Because of this, we recommended the partners to actually disable background DEX optimization before T, and the PM DEXOpt disable BG DEXOpt equal true is the way to basically disable this from system property. Then in T, we want you to bring this back to car, and what we had to do is make this kind of cancellation short so that we don't ANR the system server. So we changed the stopping mechanism to stop it immediately rather than waiting for the whole single APK to finish. And we also migrated both the background DEX optimization into idle job scheduler. So background DEX optimization actually has two jobs. One is a post-boot job, which runs always after boot up, and idle optimization, which runs in daily interval to do optimization in background. And both jobs are learning as a basically idle job, and it means it will learn when car goes into garage mode. And post-boot job runs only once after cold boot. Then there will be periodic idle jobs kicked in kind of daily interval. And the same package can run multiple times if you are using speed profile option, because speed profile optimized code with actual profile data coming from the app's execution. And if apps are basically learning different code across different run, it's also possible that background DEX optimization may run repeatedly because there may be different profiles stored. And we made both optimization post-boot and idle optimization cancelable so that it really doesn't block user switching or bring ANR to system server. And this canceling actually involves killing this DEX to auth process while it is running. So it is more kind of say brute force approach. But to prevent file system corruption, we basically create a temporary file while this optimization is going on. When that optimization is completed, then we swap this temporary file into official file so that we guarantee that there always will be some kind of working DEX optimized file in the system. And to use this for T, we need some product property configurations. As you can see, there are 4 product property configurations we are showing here. And by the way, all these are defined under package service car-base.mk file. But first one, PM DEXOpt, disable BG DEXOpt equal false. It means don't disable DEX optimization and enable background DEX optimization. The second one is a downgrade after inactive days. It basically tells how many days these basically optimized file will be kept if the app is not used. Sometimes, especially when specific car supports third-party apps, and if user does not use that app for a long time, it may be a good idea to save some space by removing them when that app is inactive. So that this basically number decides how many days the package manager will wait until it delete unused apps DEX optimized basically result. The third line, DEX auth to auth CPU set decides which CPU cores can be used. So here, core 0, 1, 2, 3, 4, 1, 2, 3 are used. So basically 4 cores are used to run background DEX optimization. Probably the system is actually 8-core system, so it is allocating about half to background optimization. There should be some CPU reserved for other process because you also run garage mode together with background DEX optimization. So background DEX optimization take all CPU away, then it can be problematic. So it's a good idea to leave some CPU cores out from here. Then last one, DEX to auth threads equal 4, specify how many threads will run. Usually you can just set this same with the number of CPU cores that you can allocate. And if you have more cores, then it may be a good idea to allocate more CPU, but you need to basically test and see if it really does not affect the other labs while learning garage mode. And also DEX optimization has other system property settings. And our recommendation for these other properties, PM.DEXOpt property is don't set it because the default setting is usually good enough. If you have a specific reason to select a non-default setting, maybe you need to do more serious testing to make sure that it really does not bring any side effects. Okay, then you enabled it, then how do you know that it's actually working in your car, right? Because it's an idle job, you can run garage mode and confirm if it's actually running or not, but running garage mode can be somewhat inconvenient. So here I'm providing some simpler way to run these jobs more explicitly. So ADB shell command, job scheduler is ADB shell command, and that through that command you can do run Android 801. So run Android 801 is basically the run idle job stored from requested from system server. Android represents system server, and ID 801 is for the post boot job. So after boot up, you need to run this once to switch into periodic optimization mode. Then once it goes into periodic optimization mode, you can do job schedule run Android 800. 800 is for periodic idle optimization job. And if you want to cancel it, basically you can also run job scheduler timeout Android command. It'll cancel all idle jobs coming from system server. You can also specify individual ID, but for your test, maybe just canceling everything is good enough. And if you want to see how DEX optimization is working in your device, you can also run this CTS test, CTS.background DEX optimization test. That test will actually learn all these scenarios for DEX optimization and confirm if the DEX optimization is actually working well in your device or not. So as a summary, background DEX optimization can now be safely enabled from Android T. So OEM can follow the configuration I've shown before to actually enable them and use it and provide a better performance for apps. And that's it for this session. Hello, everyone. In this session, we'll talk about driving safety region support from Android Automotive OS. My name is Kun Young, and I'm an engineer working in Framework team. And again, everything in this session is confidential, and everything shared in this presentation is under NDA. And this is today's agenda, so I'll explain what it means to support driving safety region, and I'll give you some example about how to use it. Then there will be some quick summary. Okay, so first, driving safety in Android. So by the way, this feature was added from Android 12 QPR1. So what is explained here is before Android 12 QPR1. So in AIOS, we have capability to block an activity if it's not safe for driving, right? So the app needs to explicitly say that, oh, I'm safe for driving by specifying this metadata called distraction optimized in its activity. If the activity does not have this metadata set, then we assume that that app is not safe for the driving. Also, we had no concept of region. For example, different countries like the US, EU, and Japan might have slightly different UI restriction or requirements on what it means to be driving safe. But we didn't have any concept of basically supporting different regions. So potentially what we assumed is that all the apps are just safe for all the regions. That was what has happened before this feature was added. And also some OEM asked us, oh, we know that this app is not safe, but if we user really wants, can you allow user to run or use this app after some warning or whatever? So essentially OEM asked us, some OEM asked us to provide a way to bypass this driving safety blocking. So from Android 12 QPR1, we also addressed this request. So then what did we do to support this driving safety region? So this feature first allows OEM to specify the current safety region, because from the car stack, we don't know what is the basically current region to apply. So that rule, we leave it to OEM layer to actually decide and tell us in which region we are in. And car framework will block the execution of current app if it does not support the current region. Previously, we assumed that all the apps are supporting all the region, but with this feature, apps can actually specify which region they are basically supporting for driving safety. For example, apps may say that, oh, my app is safe for US, but not for other region. Then one thing is that we do not define the standard safety region because we didn't have clear idea on grouping this global safety region into different country or different regions. So that thing we don't have it yet. So basically we only allow, because of that, we only allow OEMs to define their own region, and only OEMs, basically first party app knowing OEM the specific region can actually use this to basically tell that, oh, I'm only supporting specific country or specific region, while more generic third-party apps are still just saying that, oh, I'm just supporting all the regions. And we added this from Android 12 QPR1, and the API will added as hidden API now, because the main reason is that main use cases or main need for using this API is only for system app like launcher. Also, again, we didn't have a clear idea on how to define standard global region. Because of that, we decided not to make it public yet. But if we have a basically clear idea on how we can define standard region, we can make this API more official. And lastly, we added the API to bypass driving safety region so that OEM can actually allow user to run some apps if the user really wants. But because this can affect the driving safety, we basically allow that bypassing to only last until user stop the car. Once the user stop the car and display goes on off cycle, car service actually reset it. It means launch or system UI actually need to ask user again when another user comes in and starts the car again. So next slide actually shows how OEM can use this feature. First thing is that during boot up, OEM need to set this property called rlo.android.car.driving safety region. So that's the property telling in which region currently the car is running. We only define one standard value. One standard value is driving safety region.all. So this represents all region. So basically it means any app meeting any safety region will be allowed. And this property again should be set during startup because the car service reads it once during boot up. So basically it means OEM may add some kind of configuration to check this during boot up and set it once. And because this is read-only property, changing this property is not reflected dynamically. The car needs to be rebooted to actually make changes happening. And because we only define one standard region, all region, OEM actually need to define their own region using OEM's own namespace. For example, Google may define region like com.google.car.driving safety region.us. But until we define standard region in Android space, this will be only usable by OEM apps. And second thing that should happen is the OEM app need to define the region in their Android manifest to tell which region this app is supporting, right? First line, metadata distraction optimized, Android value equal true is saying that this app is supporting driving safety. So to actually declare supported region, app need to declare this distraction optimized metadata first. Then there's a second metadata, driving safety regions. This is kind of comma separated list of all the region name. Again, we don't define any standard region name. So OEM need to define the proper region names for each country or each region. Then the app should basically declare all the regions the app is supporting. And if the region is not supported, that will be the case for all third-party app. We assume that the app can support all the regions. And next slide is showing some example on how launcher can use these API to launch app or control apps, right? First line is showing that there's this API called car package manager.get current driving safety region. So this is the API to tell launcher that the selected region for current car. This is basically coming from the read-only property we have seen in previous slides. Next, launcher can query if this activity is actually allowed, is it activity distraction optimized. Basically, this call will return whether the app is safe for driving or not, considering driving safety region, and also if the app is allowed with a kind of say special excuse, this will also return true and say that this app is okay to run. And if this app is not allowed, launcher can, for example, check the supported region. So get supported driving safety region for activity as a user will return the list of all the regions that is defined for this app and this activity for the given user. And lastly, if OEM want to allow the app, even if OEM knows that this app is not safe for driving in this region, but still OEM want to allow user to use it, probably OEM may add some UI to give some warning to user. After user's acknowledgement, OEM's launcher can call this API called control temporary activity blocking bypassing as a user. So that call will basically allow bypassing this app from driving safety check, and this app will be allowed to be launched. After calling this, basically launcher can launch the activity using start activity or whatever Android API. Then the activity will not be blocked anymore. But again, this will be temporary. Once the user stops car and display turns off, this temporary waiver is reset and launcher needs later when user comes in and starts the car again. As a summary, driving safety region support allows OEM apps to specify specific regions meeting driving safety. And to make this API more widely available for third-party apps, we need some input from OEM because we want to better understand what is the best way to actually define these standard driving safety regions. If any OEM has basic input on how to define this standard region, please let us know. That will help us to actually widen this API to wider range of apps. And that's it for today. Thanks.
Hi, everyone, and welcome to our fireside chat for our day one, track one. My name is Vasco, and I'll be the moderator for this session. We'll run through questions posted throughout the day in the different sessions, and then we'll go to live questions that you'll post in our fireside chat page. So feel free to add those as we go along. So first, we'll start with some introductions. Oliver.
Hi, my name is Oliver. I'm part of the Automotive Partner Engineering team here in Munich, and I'm looking after virtualization topics.
David.
Hey everyone, I'm David, Product Manager on Android Automotive, responsible for vehicle APIs.
Nisha.
Hey everyone, my name is Nishta. I am also responsible for Android Automotive on Vehicle Actions APIs.
Young-sang.
Hi, this is Yunjia. I'm managing this product. Thank you.
Rise Against. And if someone is talking at Rise Against, the meeting room is muted right now.
Kunyang. Hi, my name is Kunyang, and I'm leading framework team. So I cover several framework issues today. Yeah.
Hi, I'm Lakshman. I'm software engineer in the framework team. My presentation is on the flash memory monitoring.
Hi, I'm Edward. I am a product manager and covering the car mainline project.
Hi everyone, my name is Yushan. I'm in the framework team. I will talk about answer the questions related to vehicle health.
Cool, thank you everyone. And we'll start actually with you, Yushan. The first question we have is when this idle vehicle hall will be rolled out?
Thanks for the question. So this AIDL vehicle hardware abstraction layer will be rolled out as part of the T release. So yeah, whenever the T release is rolled out, it will be rolled out as part of that.
Thank you. And the second question we have for you today is what is the upper limit for large data transfer in one function call?
Technically, we use a shared memory file for large data that is larger than the binder memory limitation. So it really depends on what's the size limitation for creating a shared memory file. As long as you can create a shared memory file, you can pass that data. So it should be pretty large. We haven't tried really large data, but we have tried like megabytes data, and it's definitely doable. So it depends on what's the limitation for the shared memory file.
Thank you. And two more questions on your area for now. The third one is, what is the protocol that is used for communication with the vehicle bus?
Yeah, good question. So we actually don't regulate or define any protocol that is usually used for communicating with the vehicle bus. It's vendor specific, and it can be specific to any hardware. We don't define that in the vehicle hardware HAL interface. And we ask each vendor to implement their own communication protocol with the vehicle bus in the vehicle HAL itself.
And finally, as a vendor implementation, do we need to provide support for both previous VHAL hardware binder and this new HIDL-based VHAL interface?
So for vendor implementation, if you implement the new AIDL-based vehicle HAL, you no longer need to maintain the old HIDL-based vehicle HAL. You can basically replace your vehicle HAL implementation with the new one, and you no longer need to maintain the old one. But for us, from the framework system Android side, we would support both. So if you didn't migrate now, we will still support your old HIDL-based vehicle HAL. But for the vendor, you don't need to maintain both. Once you migrate, you only need to maintain the new implementation.
Yeah, maybe I want to add one more thing. In longer term, we'll drop the support of the HIDL HAL. That time we haven't decided yet. But if you are starting Android T development, it's highly recommended to do the AIDL migration because at some point in future, we'll drop the support for HIDL HAL.
Thank you for additional detail, Kyung. So moving to V-Hall properties, does the fully charged status and EV charge remaining time consider the max charge percent property previously introduced, EV charge percent limit?
Yes. Hi, I can take this question. The answer to this question is yes. The charge remaining time is dependent on whatever percent limit is set by the user. If, for example, the client has specified, the user has specified that 90% is the limit that they have for a fully charged vehicle, then that would be considered, and fully charged will be 90% and not 100. So the answer is yes.
Thank you. And moving to car mainline, what does signed mean in the sentence Google signed car mainline modules? Are you signing the mainline modules when releasing them to preventing any code change? If yes, verify it at the compile time runtime. I know if this would be Edward or Kyung.
Yeah, I can take it. Yeah, I'm Kyung, I can take it. So, but signed means that it's the same as APK, right? All APKs downloaded from Play Store is signed with a specific key, so that the same basically key owner vendor can basically keep updating that component, right? So when we release mainline to our basically partners and OEMs, we'll basically provide Google signed pre-built so that OEM just take it and doesn't have to do anything else. Or OEM can also basically build their own basically mainline module from the source code, but OEM basically need to sign it with their own key. Probably I explained about in the AOSP, we basically use this dev key. We use a dev key, which can be problematic in terms of security. So OEM need to do additional thing to do the signing. So then what is the intention? Yes, if you take Google signed pre-built, then you really cannot do any patch. But anyway, our recommendation is we don't want the OEMs to basically keep applying, basically keep changing car services, because that change will be a continuous thing OEM need to do again and again. And if you have some changes that you need to make, and if there's a clear justification, we can work with you to figure out if we can actually take that as a kind of say, existing code inside the car service as our feature, or we can provide you some mechanism so that you can basically do it in separate APK rather than doing it in car service. And verify the compile time, runtime, we don't do any verification. So basically, the platform itself is still fully controlled by OEM. So even if OEM basically modifies the car service and do whatever changes they want to make, we don't have any enforcement to basically prevent that. But the only downside is that once we release this mainline in more regular interval than current 1 year release cycle, OEM having to apply those patches, that work will be very big. If you have many patches that should be applied for car service, which is continuously released in every 2 months or 3 months, that will be a lot of work. So we'll not do any enforcement, but really continuously doing that will increase a lot of efforts in OEM side. So maybe we really need to look into some other way to avoid that. Otherwise, integration efforts will become very huge. Yeah, that's all. Yeah.
Thank you. And the next question we have is, are dynamic RROs available in Android T?
Okay, so yeah, Mayank is out today. So again, I'm Kyung and I'll cover it. So yeah, dynamic RRO is available in Android T. And should you also cover 2 other questions? Vasco, do you want to read them?
I can read it. Does the required property must start with RO dots, or can it be like vendor dots and set on boot time?
Okay, so this is some kind of say interesting question. We intentionally selected the RO. So RO property in Android means it does not mean that you cannot set it. RO property actually means you can set it, but you can set it only once. That's our intention. So during boot time, OEM will decide which, for example, there can be multiple basically RRO in the same image, in the same image. And from the same image, during boot up, OEM may figure out, oh, in this product variation, for example, I need to use RROA. Then set that property, set the read-only property once, and set the property to use that basically package A, RRO package A. Then after that, it is no longer changeable. Yes, you can set it during boot time, but because it's a read-only property, you can set it only once. We really don't want to basically any other components during the boot up time to basically change it and bring some unexpected behavior. So we intentionally basically set it as a read-only, but our expectation is that during boot up, OEM should set it once.
Thank you. And the other question we had in this area was, can dynamic RRO override only some of the resources which are already override in static RRO?
Yes, that's the intention of dynamic, right? Because we are using this property to actually select. So basically between static and dynamic, right, the partitioning is like this, right? If you have some kind of common configuration that will be applied for all product trim, maybe you can put them into one static RRO. But there can be some configuration which can be different depending on your trim level or your specific product, right? That you should add it to dynamic RRO, so that dynamic RRO will actually override whatever configuration static RRO has. So your static RRO may have a very basic trim configuration, so that some of them may not necessarily work in some product, but in that situation, you can have a dynamic RRO to actually override that and maybe provide some kind of, say, more features or different configuration compared to static. Yes, so let's say dynamic RRO is supposed to replace and override static RRO.
Thank you. So we have a live question. I'm not sure if you have the right people in the room to answer, but I'll ask either way. This is related to text optimization, which often is a motivation for garage mode. Garage mode can require some complex systemization, especially to include all aborting use cases and suspend the RAM. Would it be better to require through CDD that job scheduler needs to be processed daily and allow OEMs to select suitable timing?
Okay, I'm Kyung-Young and I'll cover this again. So garage mode has two purposes, right? So garage mode basically allows the system to run some kind of system improvement job like text optimization. But garage mode is also a window for third-party app to actually run whatever update they need to do, like downloading some kind of data or doing some kind of heavy computing job in background. So that's why we are having this requirement for garage mode. So probably we will not add a separate requirement for learning this text optimization for job scheduler, but still anyway, intention of this garage mode is to learn this idle job for both apps and for the system. If the question is about changing CDD to actually mandate learning job scheduler instead of garage mode, maybe we can have some separate discussion. So maybe please reach out to us and we can have deeper discussion on the intention. And then maybe we can sort out if there can be some better way to address that. Yeah.
Thank you. And I think this would also be for you. So this is regarding a migration of VHAL from Heidel. As I remembered, Heidel was already being used for services when HALs were introduced. Why did Heidel got introduced as interface language for HALs instead of Heidel at the time?
Hi, this is Shan. Sorry, I think this is regarding to the history for some of the technical decision. Yeah, I can say I fully know the history. It's before I joined this team. So
yeah, maybe I'm Kyung-Young. Yeah, maybe I can answer that. So maybe this is really more about history. Why? So essentially, yes, why did we go to Heidel and now come back to AIDL, right? To be honest, when I actually talk with our Heidel team, it was a kind of our mistake. But at that time, there was also a reason. AIDL at the time basically lacked some capability, which usually is better supported in C++ world. So basically, AIDL, basically the team who basically led that design actually focused on that kind of, say, C++ specific hacking feature rather than basically having unified AIDL. So at the time, AIDL also lacked some story about providing future compatibility. So they made that decision to basically define something new. And later we found out that that's problematic. because idle is better for C++, but on the other hand, some of those idle feature which is better for C++ actually doesn't work well with Java, because some syntax like union actually doesn't work with C++, Java. So it means you define some idle, depending on what you add there, actually that idle may not be necessarily usable from Java side. So there was that kind of challenge. But because of those restrictions and problem, in the end, the team basically concluded that, oh, we'll just make this more generic enough so that we can use this for both C++ and Java. And there was some kind of compatibility thing the AIDL didn't have. So that's why they added this term stable in front. So stable AIDL is more kind of say, more well-managed. And also it has additional things there like version check, so that it can be actually future compatible. So when they added those things, then the conclusion is, okay, we should really move into AIDL. So we really don't have to basically use two different basically IDL across different layers. So that was basically the history. But anyway, short answer or short summary. Yes, we thought that was the right thing, but later we regret, and it was actually a mistake.
Thank you. And a quick note to all the viewers that we are running to the last few questions. So if you have any questions that you want to ask, this is a final call for you to put it into the site. The next question is on virtualization. Will Trout 1.0 be able to run fully virtual? If not, which devices are still run native? Is USB virtualized?
Cool. Yeah, let me take that one. So and start with the easiest part. So we do not support virtualized USB in Trout today. But more generally, our aim is to get to a place where Trout is generally fully virtualized. And you can find the list of supported devices on sourceandroid.com today, actually. So follow up. And yeah, we are working on closing the gaps here for future.
Thank you, Oliver. And a quick note to our viewers that I know that there are a lot of other questions around virtualization we're not able to answer today. Unfortunately, Enrico is not able to join, but we'll answer those offline to those who ask them. The next question is, can dynamic RROs contain only one drawable, for example, while other resources still override by static RRO?
Besides static and dynamic, right, you can actually have multiple RRO packages in the system. And probably Mayank's presentation talked about priority, right? In the end, dynamic RRO has a priority over static. But even basically among the static item, you can use priority. So that, for example, some RRO may set from the SOC vendor, so that they set some configuration that makes sense for SOC vendor, then may have lowest priority, right? Then tier one may have some kind of say priority. We have some recommended range. So maybe override what SOC vendor is set. In the end, OEM may override it. Right? So we basically expect there will be multiple RRO in the system. And basically our recommendation is use the allocated priority range so that you can basically decide which one will actually override others. Right? So one RRO can basically override, may only contain specific basic configuration. Other RRO may have other configuration, but when there's a conflict, whatever with the higher priority wins. Also other basically priorities that dynamic RRO wins over static. That's why we are using static as a last mechanism to do this kind of say product trim level configuration, because even the same image, there can be different configuration, so that can be basically finally selected by dynamic RRO. So yes, it's intended to have multiple RRO in the system, and we have a priority, and also we have a static versus dynamic to finally decide which one wins. But there's only one configuration in one RRO package, then that will just be the configuration for the device or product.
Thank you. And a last minute question. So there are multiple other HALs too, camera, EVS, etc. Is there a plan to migrate them as well to Heidel?
Okay, so I'm Kenyang. Maybe I'll take this again. We didn't set the timeline, but currently we have basically clear intention and request from our basically HAL management team to migrate all HAL from idle to AIDL for all automotive HALs. So probably if you take a look at Android T, we actually have already migrated a lot of HALs. We only have a few HALs left as idle, and those HAL will migrate in Android U timeframe. So hopefully from Android U, maybe OEM, especially starting a new development or associate vendor starting a new development, we really recommend to develop only AIDL HAL rather than idle HAL, because AIDL HAL in longer term, idle HAL in longer term will deprecate all of them. But in short term, as Sean said, in vehicle HAL, we'll support both for compatibility, because when OEM update all the BSP with basically new Android releases, we don't want to basically break things up. So we'll basically keep supporting both HAL for a while. But after some time, by the way, we haven't decided when, but after some time, we'll drop support for this, all the idle HAL, and ideally all HALs we use for Android Automotive should be only AIDL HAL. That's our kind of our longer term thoughts. But we'll share further detail when we actually set specific timeline and milestone. Probably that may be the topic for next year's bootcamp.
So thank you for that answer. And I think with this, we close the questions that were asked for today. Thank you to all the panelists for the answers. Thank you for those last questions. And if you have any further questions, please post them on the page. We'll continue to answer them offline. Have a great day and hope that you can join us tomorrow as well.
Thank you.
Thank you.
Thank you.
Thank you.